బుజ్జాన్ని పంపి ఫస్ట్ పిల్లలకి ఎంత కొడతావులే
Good evening to Ananda. Good evening. Good evening to Ananda. So I already informed to you people in Telegram that the class will start at 5:30. Yes, I think so. Yeah, fine. So anyhow, it was a bit delayed further because there is a network issue for me, internet issue. So that was clear now. Okay, fine. Fine. So let's see the review of the previous class, what we have studied. Just we have taken some calculations on three-phase short circuit fault on a no-load operating alternator. And then we have done that short circuit fault study on the loaded system also, which is nothing but simply addition of the load current to the fault component current. That's it. Okay. So now we are taking up the single line to ground fault analysis. Already we said different types of faults, right? Like we have LG, LL, LLG, triple L, and triple LG. Okay. So I'm going to take up the first type of fault what we have given in the list, that is single line to ground fault. Okay. So the next heading here is single line to ground fault. Ground fault. Else you can say it is LG fault simply, or phase to ground fault also you can say. LG fault, else you can say phase to ground fault. Yeah. See, first of all, listen to this. First of all, see anything, any type of fault what we are going to study further. Is it LG, LL, LLG? First, what we'll do is we'll take only one alternator. No load operating alternator will take, and then we'll take a fault on that alternator terminals, and we'll do that fault analysis. After that, we will extend that. We will extend that to do that fault analysis for fault at any point on the system. So this is the way how we are going to discuss further. I think all of you getting my point what I said now. First, I'm going to take a no load operating alternator. We'll finish the LG fault analysis on the no load operating alternator. Then we are going to do some sort of generalization to calculate that LG fault current for the fault at any point on the system. Okay, so I'm taking no load operating alternator just as a three-phase network symbol like this. Okay, so it was alternator. Here showing, and it was neutral. These are the outcoming terminals ABC. These are the outcoming terminals I'm calling as ABC. Okay, and this neutral is connected to ground with an impedance of Zn here. Neutral is connected to ground with an impedance of Zn. Okay, these are the phase A, phase B, phase C induced EMFs. And you know this generator is having positive sequence impedance per phase Z1, negative sequence impedance per phase Z2, zero sequence impedance per phase Z0. Already in the previous classes, maybe in the sequence networks construction, we discussed that Z1 is nothing but simply JXD double dash we have to consider, because our interest is to find a subtransient fault current only. And I said already in the examination, if you ask to calculate simply fault current, we should give the answer as subtransient fault current. Okay, so Z1 value JXD double dash, Z2 is JXD double dash plus JX2 double dash by 2. Z0 is JXL. These terms I think you have remembered. Okay, now these are terminal voltages we are showing VA, VB, VC. Terminal voltage we are showing as VA, VB, VC. And internal voltages we have EA, EB, EC. Internal voltages EA, EB, EC. Okay, fine. Next. Currents in the alternator terminals are IA, IB, IC. Currents in the alternator terminals are IA, IB, IC. Okay. Next thing. Next thing. So before taking up this fault, the alternator is under no load condition. So first I want to write those pre-fault conditions. pre-fault conditions. Yeah, so let's take pre-fault conditions here. Pre-fault state of system. No load, simply no load. Okay, no load in the sense, phase A current is 0, phase B current is 0, phase C current is also 0. All the three phases currents are zeros. IA equals 0, IB equals 0, IC equals 0. Not only that, whatever the terminal voltage you have, so-called VA, VB, VC, these are nothing but internal voltages of the alternator. So you can write VA equals to EA, VB equal to EV, VC equal to EC. Terminal voltages are nothing but internal voltages because you don't have any current flow in the alternator. So no voltage drops here. So obviously terminal voltage and internal voltage will be equal. And how these three internal voltages will be here? How are these EA, EB, EC values? Whether these are balanced or unbalanced for you? How are these EA, EB, EC? That will be obviously balanced. Okay. So these are balanced voltages, we can say balanced voltages. And if these are balanced voltages for you, if you convert these balanced voltages into symmetrical components, balanced voltage into symmetrical component, you will get only positive sequence component EA1 and negative sequence and zero sequence components will be obviously 0. Negative sequence component is 0 as well as zero sequence component is also equals to 0. Okay. EA1 equals to EA, EA2 equals to 0, EA0 value is also equals to 0. Okay, next thing. See, whatever the EA1 is equals to EA we have, EA1 is equals to EA, that itself we are going to name as pre-fault voltage of the system. Pre-fault phase A voltage of the system or at the fault location or at the terminal of the alternator. Okay, so I can write here pre-fault voltage, particularly I am saying with respect to phase A here, VPF is equals to EA1, which is nothing but EA. Pre-fault voltage equals to EA1, which is nothing but EA. Nothing but EA. Yeah. Next thing. Now let's take fault at phase A, means phase A to ground I am taking that fault. Simple, very simple. Phase A to ground fault we are considering solid fault. Solid fault means there is no fault impedance at all. There is no fault impedance. With fault impedance, how to do this? We'll take that one later. Yeah. For time being, solid LG fault. Solid LG fault at alternator terminals. See, after having this solid LG fault on the alternator terminals, what is this phase A voltage we can experience now? What will happen to this VA value? It will be automatically become 0. VA value becomes 0. Okay. So after saying that this VA is 0 and we have a potential gap, and definitely this IA current will be non-zero. IA current will be non-zero, and that current will flow into the fault element obviously. So I can say that fault current and phase A current both will be exactly equal. Fault current and phase A current, both are exactly equal just by the application of KCL at this node. IA is entering, IF is leaving, so IA is equals to IF we can see. Okay. What about this B and C currents now? What about the currents in the phase B and phase C? Those currents will be 0 only because those are experiencing open circuit. So obviously phase B current is 0 and phase C current is also equals to 0. Okay. What about the phase B voltage after the fault occurrence? What about the phase B and phase C voltages after the fault occurrence? We don't know. Because this B is not connected to any other part of the system. C is not connected to any other part of the system. So I don't know the values of VB and VC, but expecting that these two voltages will be not equals to 0. Expecting that these two voltages will be not equal to 0. Now I will write all the things, whatever we have observed during short circuit fault. Okay. So first of all, voltages if you consider, phase A voltage is equals to 0. B voltage, we don't know, non-zero it is. C voltage, we don't know, that's also non-zero. And if you think about the currents, phase A current is nothing but fault current only. Phase A current is nothing but fault current only. B current is 0 and C current is also equals to. See, in the pre-fault condition, means before occurrence of short circuit fault, the system is balanced state. System is under balanced state. Now, as if the voltage and currents are coming like this, obviously the system will be moving into unbalanced state, we can say. So by means of this, you can say system is unbalanced. System is unbalanced. By means of that, we can say system is unbalanced. Okay, fine. How to do this unbalanced system analysis? How to do this unbalanced system analysis? Just recall the steps to be followed for the unbalanced system analysis. We discussed that at the end of the symmetrical components theory. Second chapter, at the end of the second chapter, we discussed about what are the steps to be followed in the analysis of the unbalanced system. Just go through those steps. Okay, step number one. Convert ABC voltages and currents into symmetrical components. Convert ABC voltages and currents into symmetrical components. That's the step one. Step two. Step number two. Get some relationship between the symmetrical components of voltages and symmetrical components of currents. That is the second step. Third step. Construct positive, negative, and zero sequence Thevenin equivalent networks with respect to the point of unbalance. The point of unbalance is nothing but fault here. Means fault location. With respect to fault location, we should construct the positive sequence network, negative sequence network, as well as zero sequence network. And then we have to give the connections by following the what we call relations what we have obtained. Okay, that's okay. But it may be confusing you because all the statements I am saying at only one point. But if you have those steps with you now in your notes, just go through those steps. And how I am implementing those steps, that you have to follow. Okay, yeah. So first I am taking up conversion of these voltages and currents into symmetrical components. First I will take symmetrical components for currents. Very simple. Symmetrical components for currents. So I am showing here IA0, IA1, and it is IA2 sequence currents equal to 1 by 3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha. Have you remembered this matrix? In the symmetrical components, we have discussed about this matrix, right? IA, IB, IC. Yes or no? I think all of you remember this matrix. I need your response. Please kindly respond. Do you know this matrix? Yeah, good. Next, listen here. Next, see, from the present unbalanced condition, IA current is existing. It is not zero. B current is 0. C current is also 0. Now, by following the matrix multiplication, you find out what is IA0, IA1, IA2. Okay. What is IA0 current from this? 1 by 3, IA plus 0 plus 0, it will be IA by 3. What is IA1 current from this? 1 by 3, IA, 1 by 3, IA, means IA by 3 again. This also 1, IA by 3. This also you get as IA by 3. Okay. What is IA2 current? IA2 current, it will be again 1 by 3, IA plus 0 plus 0. This current is also IA by 3. Now, what is the relationship you get between these three? What is the relationship between these three currents now? All the three sequence currents are equal. So IA0 equals to IA1 equals to IA2. IA0 equals to IA1 equal to IA2. This number we are going to say as phase A current by B. That is the relationship between the symmetrical components of the currents. Okay, all the three symmetrical components of currents are equal. That will be equals to IA by 3. Okay, next one. Symmetrical components for voltages you have to do, and you have to apply the relationship between the symmetrical components of voltages from that. Yeah, please complete it quickly. I will move with the next slide to take up at symmetrical components for voltages. Simple, very simple. Just follow the procedure. To do any unbalanced system analysis of this kind. Okay. So I'm saying here symmetrical components for symmetrical components for voltages. Symmetrical components for voltages means VA0, VA1, VA2 one side equal to that A inverse matrix 1/3, 1, 1, 1, 1 alpha alpha square, 1 alpha square alpha multiplied with VA, VB, VC voltages. Multiplied with voltages like VA, VB, VC. Okay, next thing. From this VA, VB, VC values, you know already VA value was 0. VB should keep as it is. VC also you keep as it is. VA value 0, VB you keep as it is, VC also you keep as it is. We don't know about VB and VC numbers because those are open circuit. I don't know those voltages. Okay, now by matrix multiplications here, matrix multiplication, what is the zero sequence voltage VA0? 1/3, 0, VB, VC. So it will be 1/3, VB plus VC we are going to 1/3, VB plus VC we are going to next. Positive sequence voltage how much? 1/3, 0, alpha VB plus alpha square VC. And negative equals to what you get now? 1/3, 0, alpha square VB plus alpha into VC. Alpha square VB plus alpha into VC. Like this, we'll get voltages for phase A symmetrical components, right? VA0 we got, VA1 we got, as well as VA2. But one thing, anybody, please tell me, do you get any relation between these three voltages now? Just by looking at these equations, is it possible to say that there is a relation existing between these three voltages? No, we can't say. We can't say exactly from this. But one thing is clear that already you know phase A voltage is 0, right? Already you know phase A voltage is 0. See, if phase A voltage is 0, then VA0 plus VA1 plus VA2 that will be equals to 0. Means sum of the symmetrical components of phase A voltages, will be equals to 0, we can say. Okay, so I'll write here as phase A voltage is equals to 0, we can write VA0 plus VA1 plus VA2, this summation is equals to 0. VA0 plus VA1 plus VA2, that summation will be equals to 0. I think step 2 we have completed. First, we converted ABC components to symmetrical. Second step, got the relationship between the symmetrical components of voltages and currents. Like this we got. Next step, we should construct positive sequence Thevenin network, negative sequence Thevenin network, zero sequence Thevenin network with respect to point of unbalance. Okay. See, listen here. See, after all, we have a simple alternator here. And on that alternator, phase A to ground fault was occurred. Again, I'm asking you same questions. Sequence networks construction will be done with load or without load. Means what is the load right now? Fault. Fault element is a load for me. Zero impedance load it is. Okay. Now I'm repeating the question. What I'm saying with respect to fault location, can be constructed before occurrence of fault or after occurrence of fault. Before fault or after fault? Anybody please tell me. Sequence networks are constructed before fault or after fault? Before fault only, not after fault. All of you saying after fault here. Some before also. We have to construct the sequence networks before the fault occurrence, and we have to give connection among them by following the conditions obtained during the fault. Just like Thevenin equivalent circuits. When we construct the Thevenin equivalent circuit, before keeping the load only, right? Means before occurrence of the fault, we should be ready with the Thevenin equivalent circuits. Okay? With respect to point of unbalance means should concentrate with respect to fault location only. So simple. With respect to fault location, I will see we have only one generator. How you represent the generator in the positive sequence? Voltage source EA1 with a Z1 impedance. Negative sequence, only Z2 impedance. Zero sequence, up to neutral, Z0, neutral to ground, 3Zn. That's it. Those three circuits will draw now. Okay? Yeah. So let's say sequence networks. Sequence networks. Construction is done in pre-fault condition. If you want, you write in bracket for your clarity. First one, positive sequence network. Positive sequence network. So we have only alternative, right? So this is the positive sequence network. Neutral, and this is a pre-fault voltage EA1. Okay, and this is a positive sequence Thevenin impedance Z1, and this is a positive sequence terminal voltage VA1. Current is IA1. Okay. Negative sequence network. Negative sequence network. And we have only Z2 here, so called negative sequence impedance. And neutral. And it is a voltage. I'm saying it is VA2. And this current is IA2. Like this will have. And you know, this is the fault location. This is the fault location. F. Okay. Next one. Zero sequence network I'll draw. Zero sequence network I will draw. So up to neutral, we should keep zero sequence impedance of generator Z0. Neutral to ground, we should keep 3 times of Z. You keep this as 3 times of Z. Okay. And this terminal point is a fault. This is VA0 value. And this current I am showing as IA0. Okay, and this is our fault location F I am showing. Fault location F. Okay. Next step is we have to give connection among these sequence networks by following the relationships what you obtained during the short circuit fault. Means after creating the short circuit. Just look here. See, after creating short circuit fault, which condition we have to follow mainly? Is it voltage condition or current condition? That's the question. What condition I have to follow mainly while we are giving the connection? While you are giving connection between the sequence networks, what condition I should follow strictly? Is it voltage condition or current condition? Voltage condition. Voltage condition. All of you saying current. Voltage condition we have to follow. Why? Why we have to follow voltage condition? Huh? Because whatever may be the current values doesn't matter. As if we have phase A to ground fault, phase A voltage will be 0. That's it. So we have to follow voltage conditions mainly. Voltage conditions mainly. Okay, what is that voltage condition we have? VA0 plus VA1 plus VA2 equals 0. Means we should keep these three circuits in such a way that sum of these three voltages, VA1 plus VA2 plus VA0 is equals to 0. Such that we should give the connection. Okay, so let me take next slide. Sequence networks connection. Sequence networks connection. Connection according to the conditions. Let's copy positive sequence network first. Right, so it's a positive sequence network. Just observe here once. Okay. Next, negative sequence network I am showing. Negative sequence network. So this is a negative sequence network for you. Next one, zero sequence network I am drawing now. Zero sequence network I am drawing like this. Okay. So this is our zero sequence network constructed with respect to location of short circuit fault. Okay, so this is a location of fault as we have mentioned just now. Now simply we should sum up these three voltages. VA1, VA2, VA0 voltage we have to sum up. See, to sum up those voltages, I should join these things in this manner. Okay. So if you join like this, if you sum up these three voltages in this manner, then obviously this resultant voltage here comes to be VA0 plus VA1 plus VA2. VA0 plus VA1 plus VA2. How much is that voltage he is saying here? How much is that voltage? VA0 plus VA1 plus VA2. That is 0. How to make that one 0? To make that one 0, we should keep one short circuit across this, such that this summation of the three voltages will be resulting to be 0. Okay. Summation of the three voltages will be equals to 0. And we have to check the current condition also now. What is the current condition we have? IA0 equals to IA1 equals to IA2, which is IA by 3. Check back to this diagram. IA0 is the current flow in the zero sequence circuit. Same current will flow in the negative sequence circuit. Same current will flow in the positive sequence circuit also. Means current flowing in this loop is nothing but either positive sequence current or negative sequence current or zero sequence current. All the three sequence currents are one and same. That condition also we have implemented in the model. Means while you are doing solid single line to ground fault, all the three sequence networks should be connected in series. The three sequence networks are connected in series. Across that series connection, we should keep a short circuit. That statement you have to remember. Okay, so the three sequence networks, are connected in series. Okay. So after obtaining this sequence networks connection, next step is what? Do the network analysis. By doing the network analysis, what you have to calculate actually? We have to calculate sequence currents IA1, IA2, IR, as well as sequence voltages at the fault location. What are the things? VA1, VA2, VA0. Okay. See, listen all. What is this EA1 name? Anybody? Just a cross check. Please tell me. What is EA1 name? Positive sequence pre-fault voltage. VPF. Sometimes you can call that as VPF1 also. Okay. Next thing. Why don't we have that pre-fault voltage in the negative sequence circuit? Why don't we have pre-fault voltage in negative sequence circuit and zero sequence circuit? Why we have that only in the positive sequence circuit? Anybody? Tell me the answer. Because the pre-fault system is balanced. As a pre-fault system is balanced, you get the pre-fault voltage only in the positive sequence network, and you don't have that in the negative and the zero sequence networks. Okay, simple. We'll do network analysis now. Network analysis is the next heading, I can say. Network analysis is the next heading. First, I'll calculate sequence currents. Tell me, all the three currents are equal from the circuit. See, once after giving the connection, that is your way how you redraw the network and all. That is your way how you are going to redraw the network and all. See, I feel that all these impedances in the loop are in series with only one voltage source. So that voltage source by the total impedance is a current flow in the circuit that is nothing but any one of the sequence current. So I can write by network analysis. IA1, IA2, IA0. All the three currents are equal to pre-fault voltage EA1 by sum of the impedances Z1 plus Z2 plus Z0 plus 3Z. Z1 plus Z2 plus Z0 plus 3Z. That will be the sequence current. And this VA1 you can replace with VPF if you want. Or you can say positive sequence Thevenin voltage also. That term also same. Positive sequence Thevenin voltage also you can write. That's your wish. Okay, next one. Next, let us take up the sequence voltages quickly. After that, we will go for ABC components. Sequence voltages. What is VA1 here? VA1. You apply KVL for this loop. What is VA1? Pre-fault voltage EA1 value minus IA1 into Z1. Okay. VA1 is equals to EA1 minus IA1 into Z1. Okay. Next, what is VA2 value? What is negative sequence voltage VA2? Nothing but minus IA2 into Z2. Minus IA2 into Z2. Minus IA2 into Z2. That's the negative sequence voltage. And what is zero sequence voltage? Minus IA0 into Z0 plus 3Z. Minus IA0 into Z0 plus 3Z. That is nothing but the zero sequence voltage VA0 we are writing here. Okay. Right. Simply you convert these sequence components into ABC components. Convert these sequence components into ABC. Let's move to the next slide. Right. So I'll say here ABC voltages and currents. ABC voltages. First, I'll say ABC voltages here simply. What will be that VA value? VA in terms of symmetrical components, in terms of symmetrical components, nothing but VA0 plus VA1 plus VA2. And if you calculate this number, it will come to be 0. Because you know already, as a fault is a solid fault, phase A voltage will be equals to 0. Phase A voltage will be equals to 0. That's it. Okay. Next thing. What is phase B voltage? What is phase B voltage? Anybody? We can't get direct number. I'm not getting. The equation will take care how to get that VB value. What is the equation now? 1 by 3 VA0 plus alpha VA1 plus alpha square VA2. 1 by 3 VA0 plus alpha VA1 plus alpha square into VA2. Following correction. So simply you calculate these sequence voltages. After calculating the sequence voltages, dump these sequence voltages into this VB equation. That will give you phase B voltage after occurrence of short circuit fault. Okay. What is phase C voltage after the occurrence of short circuit fault? 1 by 3 VA0 plus alpha VA1, sorry, alpha square VA1 plus alpha VA2. Yeah, I'm sorry. It's not 1 by 3. I committed a mistake. I'm really sorry. So I have written reverse equations. I'm really sorry. Yeah, VB value will be VA0 plus alpha square into VA1 plus alpha into VA2. This was the equation for the phase B voltage. That was the equation for the phase B voltage. Yeah, and VC will be VA0 plus alpha into VA1 plus alpha square into VA2. Like this, you will get the B and C after the fault occurrence. Next, what are the ABC currents for you? What are the ABC currents? Very simple to write. ABC currents. What is phase A current? Generally, we say phase A current. IA0 plus IA1 plus IA2. IA0 plus IA1 plus IA2. But you know already all the three sequence currents are equal. IA0 equals to IA1 equals to IA2. Na? You write this as 3 into IA0. Else you write this 3 into IA1. Else you can take this 3 into IA2. Like this you can see. All the three are equal. Positive, negative, zero sequence currents are equal. So it can be written as 3 IA0, or you can say 3 IA1, or you can say 3 into IA2. Okay, fine. Next, let's write this IA0. Already you have found that equation, right? That equation we will substitute for this IA0, and we can take the phase A current. Okay, yeah. So phase A current is nothing but 3 into pre-fault voltage EA1 by Z1 plus Z2 plus Z0 plus 3Z. Z1 plus Z2 plus Z0 plus 3Z. Now we can say 3 IA0 as a ground current. We can say 3 IA0 as a ground current. Okay. Next, what about the phase B current again? That will be 0. From original network itself, we can say IB equals 0. Else, if you are getting a doubt, use the formula. What is IB? IA0 plus alpha square IA1 plus alpha IA2. IA0, IA1, IA2 are equal. Na? You take that IA0 common. 1 plus alpha square plus alpha, that is 0. So phase B current will be 0. And phase C current is also 0. Phase C current is also becomes 0. Phase B current and phase C current both will become 0. Okay. Next thing. What is fault current? What is fault current? Just look at this model. What is fault current here? Just by application of KCL, I said. Just by the application of KCL, this fault current is nothing but phase A current. Fault current is nothing but phase A current. Not only that, whatever the current flowing into the ground, so-called fault current, that is circulating back in this manner. See, this fault current, ground current, neutral current, all the three are same in this particular short circuit fault. Application of KCL is saying that. Application of KCL is saying that for us. Okay, so I can say here fault current IF is nothing but phase A current, or you can say ground current also, both will be same. Or you can say this as ground current also. Ground current. Okay. So this is already you know formula 3 times of zero sequence current, nothing but 3 times default voltage by Z1 plus Z2 plus Z0 plus 3Z. Like this, we are going to get the fault current. Okay, fine, good. Simple, very simple one, very simple one. Next thing. Let us take up that single line to ground fault. Single line to ground fault after taking short with fault impedance. Means ZF not equal 0. With a fault impedance, ZF not equal 0. How will be these these calculations will be? Okay, yeah. Let's move to the next slide. LG fault with non-zero fault impedance, I can say. Yeah, I'm taking up this LG fault with non-zero fault impedance, means ZF value not equals to 0. Single line to ground fault with fault impedance not equal 0, or you can say ZF value not equals to 0. Okay, now I will draw same alternator diagram here, 3-phase alternator. This is the 3-phase alternator. Okay. And that neutral is connected to ground with an impedance of ZF. If it's a solidly grounded neutral, you will keep that ZN value 0, no issue. Okay. So these are outcoming terminals, and these are ABC. Okay. Next, these are internal voltages. You know, EA, EB is as it is of previous one. Okay, as it is of previous one. Phase A voltage, phase B voltage, similarly phase C. And currents, you know, here IA, IB, IC. Currents are IA, IB, IC. Phase A, phase B, phase C currents, you have IA, IB, IC. Next thing. Default conditions. Default condition, same. No load operation. All the 3 currents are 0. Terminal voltages are nothing but internal voltages of the alternator. Terminal voltages are nothing but internal voltages of the alternator. Yeah, look here. Default. No load. All the 3 currents 0. IA, IB, IC currents are 0. Phase A terminal voltage EA. Phase B terminal voltage EB. Phase C terminal voltage EC. If you convert these voltage into symmetrical components, if they are as these are balanced, you get like this. Same thing. And whatever the EA1 we get now, this itself we can say pre-fault voltage. Pre-fault voltage. VPF. Default voltage we are going to call as VPF. Okay. Next step. LG fault on phase A. Phase A to ground fault with a fault impedance of ZF. Next case. Touring fault. Touring fault means LG fault with ZF from phase A to ground. From phase A to ground. Single line to ground fault with ZF from phase A to ground I am saying. Okay. So I will show that here. This is the phase A terminal that is connected to ground with a impedance of ZF. What might be nature of this impedance we can experience? What might be the nature of this impedance we can experience? Anybody? What might be the nature of this impedance? Sometimes resistive. Most of the times, of course. Because if you have a single line to ground fault, mostly it will be a insulation flashover fault only. If it is an insulation flashover fault for you, it will be an arc. Arc in the sense it will be in the nature of resistive. So this fault impedance practically most of the times might be in the nature of resistive. Okay, but sometimes in the exam, they will say in the nature of reactance also. Sometimes they will say resistance also. That depends. Okay, but anyway, practically speaking, ZF is in the nature of resistive. Okay, now you please tell me, after this fault has been occurred, this ZF will carry a current of IF, fault current, which is nothing but phase A current only. What about phase B and phase C currents? Will be zero. Now, what will happen to voltages here? What is VA? VA equals to simply IF into ZF. Else you can say IA into ZF. VB, I don't know. It is open, non-zero. What is VC? I don't know, non-zero. Let me write. Phase A voltage is nothing but IA current into ZF, or else IF into ZF also you can say. Phase B voltage, I don't know. Phase C voltage also I don't know. Phase B voltage I don't know. Phase C voltage also I don't know. Phase A voltage is IF into ZF. Okay. What about currents? IA, it is non-zero current, which is fault current also. Phase B current, 0, open circuit. Phase C current, 0, open circuit. Phase B current is 0. Phase C current is also 0. Okay, next thing. See, if you are very clear about this, at least one fault analysis, what I am discussing thoroughly. If you are clear, the same steps you can repeat for the remaining fault analysis also. Okay, tell me, already you have these conditions with ZF equals to 0, right? Let me take up. See, these are the conditions we have with ZF equals to 0. These are the conditions with ZF equals to 0. Just for your reference, I am copying those terms. Okay. Just look here. These are the voltages and currents with ZF equals to 0, and these are with ZF not equal to 0. Which relations are looking at same here? Okay. For your information, if you want, I will write here IA equals to IF, which is non-zero. Which relations are looking at same here? Please, currents relations will be remain same. We have a change in the voltage relation. So that's why. Anyway, I will clear this. It's not needed for me now. Yeah. So I'm going to tell now. By converting these currents into symmetrical components. So-called IA equals to IF and IB equals to 0 and IC equals to 0. If you convert these things into symmetrical components, what is the relationship between the sequence currents you can obtain? What will be the relationship between the sequence components you can obtain? Anybody please tell me? All the three sequence currents will come equal. Yes or no? You have to repeat the similar steps. That's why I am making that a bit short here. Okay. So if you convert these currents into symmetrical components in the similar way of previous one, maybe this type of equations, right? Finally, you can get IA naught, IA1, IA2, all the three are equal to IA by 3 confusion. IA naught equals to IA1 equal to IA2, which is IA by 3, or you can say fault current by 3, which is nothing but fault current by 3. Okay, fine. So, but you have a difference in the voltage relation, right? Earlier, what you have VA equals to 0, VA equals 0. That's why you have written VA0 plus VA1 plus VA2 equals 0. But now that VA equals to IA into ZF. So, as that voltage VA equals to IA into ZF, I can write now VA0 plus VA1 plus VA2, VA0 plus VA1 plus VA2 equals to IA into ZF. What you can write this IA? What you can write this IA? You can write that as 3 into IA naught here. You can write that as 3 into IA naught into ZF. This will act as relationship between symmetrical components of voltages and the currents. Okay, now simply you have to implement these relations. You have to implement these relations into the network connection. Network connection. Positive sequence network, negative sequence network, zero sequence network. Now, already I said you should sum up all the three voltage drops. Earlier also we have done the same thing. By connecting the three sequence networks in series, we have taken the summation of three voltage drops. But it is zero earlier, we have made a short circuit. But now that number is non-zero. Now that number is non-zero. We should modify it. Okay, let's take sequence network connection. Sequence networks connection. Directly I'm saying, I am not writing sequence network construction, then connection. I'm saying directly connection. Okay, so first positive sequence network. Positive sequence network, and this is a neutral, and it is a prefault voltage EA1. Positive sequence impedance is Z1, and this terminal voltage you have EA1. Current here is IA1. Negative sequence network for the generator only. Only one element you have, right? That is generator. Z2, and this is a neutral, and this terminal voltage, you know, it is VA2, and this current is IA2, and zero sequence network up to neutral Z0, neutral to ground 3 times of ZN, 3 times of ZN, and this voltage is VA0, and this current is IA0. Okay, now we have to sum up these three voltages, means we should add the three sequence networks, something like this. Okay, so by adding the three sequence networks like this, you can get this voltage as VA1 plus VA2 plus VA0. You can get this like VA1 plus VA2 plus VA0. And how much is this value? How much is this value? He is saying it is non-zero. Non-zero, moreover, it is 3 IA0 into ZF. Yeah. One more thing. Kindly listen. Kindly listen. See, as it is non-zero, we have to fill this gap with an impedance. Just keep some impedance, whatever it is. So I'll say, as it is non-zero, we should fill this gap with some impedance, something like this. We have to decide what is that impedance value and all. What is current flow in this loop? What is the value of current flow in this loop? That is IA1, IA2, IA0. All the three are equal. IA1, IA2, IA0. All the three currents are equal. Okay. Now, what is that voltage drop here? VA1 plus VA2 plus VA0 is equals to 3 IA0 into ZF. Na? 3 IA0 into ZF. But current flowing in this loop is only IA0. That's why I will rewrite this like IA0 into 3 ZF. There is no mistake. IA0 into 3 ZF. By that way, I will keep this impedance as 3 times of ZF here. I will keep that impedance as 3 times of ZF. That's it. Okay. So this is a way how we are going to get that equivalent. 3 times of ZF. Vishwanathan Sai. Have you understood this? You said 6 times. It won't be 6 times. It will be 3 times of ZF we have to keep because of the IR0 current flowing. So whatever the fault impedance we have from phase A to ground, it appears to be 3 times of that in the per phase sequence networks connection. The per phase sequence networks connection, particularly for single line to ground fault. If you want to write that statement for your examination, the fault impedance in bracket ZF in LG fault appears to be 3 times in bracket 3 ZF in per phase sequence networks connection. Per phase sequence networks connection. In the per phase sequence networks connection, it looks to be 3 times of the ZF. How 6 only? How 6 only? Can you please elaborate it? How it is 6? Yeah. Next you can say, again, you have to find out sequence currents, IA1, IA2, IA0 from this one. Then sequence voltage, VA1, VA2, VA0, and convert them back into ABC. And then you make some comment on the fault current part here. That fault current is nothing but phase A current. Okay. So let's take first network analysis means sequence currents calculation. Sequence currents calculation. So all the 3 sequence currents are equal. IA1, IA2, IA0, all are equal. And that will come to be pre-fault voltage EA1 by the whole impedance of your network, Z1 plus Z2 plus Z0 plus 3Zm plus 3 times of ZF you can use. Z0 plus 3Zm plus 3 times of ZF. Like this. EA1 by Z1 plus Z2 plus Z0 plus 3Zm plus 3 times of ZF. All the impedances are connected in series. Okay. Next thing. Sequence voltages will write. Quickly. We'll take up sequence voltages. Yes, a phase A current itself is a fault current. Yeah, yes, Vaishnavi. Because of ZF value, that resultant fault voltage may not become 0. Yeah, so I can write sequence voltage here. Sequence voltages. Simple. VA1, positive sequence voltage. Just by applying KVL for positive sequence loop, EA1 minus IA1 Z1. Similarly, VA2 and VA0 you can write. Easy. EA1 minus IA1 into Z1. Next, negative sequence voltage VA2 minus IA2 Z2. Zero sequence voltage VA0 minus IA0 into Z0 plus 3Zm. Z0 plus 3Zm. Okay. So ZF is not there in considering only at phase A. It is ZF, but total system symmetrical components, it becomes 3ZF. That's what I also said. Okay. Yeah, so I'm showing 140 previous slide. If there is any lag, please complete it quickly. 140 slide I'm showing you. Yeah, next one. Sequence voltages. Now I'll say ABC currents quickly. ABC currents means actual currents which we need to know, based on which we need to design the breaker and all. Okay, ABC currents means first of all phase A current, which is IA0 plus IA1 plus IA2. All the 3 are equal, we know. IA0 plus IA1 plus IA2, which is nothing but 3 times of zero sequence current, or you can say 3 times of positive sequence current. All are same, we have written. So it is 3 times pre-fault voltage EA1 by what you can get here. Z1 plus Z2 plus Z0 plus 3ZN. Z1 plus Z2 plus Z0 plus 3ZN plus 3 times of ZF. Plus 3 times of ZF. Like this, you can get the phase A current. And obviously, phase B and phase C currents are 0 because of open circuit. Phase B current is 0, phase C current also 0. And similarly, if you want to write ABC voltages, equations only. ABC voltages, equations you can write. Yeah. Moving to the next slide. So if you write ABC voltages, simple equations only, because we don't get the prescribed value in terms of symmetrical components here. That's why I'm going with equations to calculate ABC voltages. Phase A voltage. VA0 plus VA1 plus VA2. That's it. Phase B. Already have VA0. Alpha square VA1 plus alpha into VA2. Phase C voltage. VA0 plus alpha into VA1 plus alpha square into VA2. Alpha into VA1 plus alpha square into VA2. That's it. Okay. Next one. So next we will think about the selection of circuit breaker rating. Selection of circuit breaker rating based on single line to ground fault analysis. See, actually, breaker rating is selected based on the most severe fault, as we said earlier. Breaker rating is going to be selected based on the most severe fault, as we said earlier. I no need to bother about that condition now. Simply in the exam, if they are asking you, find out the three-phase circuit breaker rating. Find out the three-phase circuit breaker rating if the for single line to ground fault on the system. If that's the question given, how to calculate the rating of the breaker? Okay. Before moving to that breaker rating, let me generalize this. So till now, we have taken only one alternator and we have calculated the fault currents and all, right? So fault current and the phase A current both are equal, I said earlier also. Fault current and phase A current both are equal. Now we are going for generalization. After doing generalization, I will go for breaker rating. Then I will move to short circuit capacity of the system for single line to ground fault. Okay. So let's take first generalization. 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 Look here. Very simple to write. So I'm showing some network here, generator. You have some transformer here. And this is some transmission line wire connected to some big power system network. Big power system network. And at this bus, there exists one more line, one more transformer, and this is one more generator existing like this. This is some big power system. This is a big power system consisting of a number of buses along with number of generators, transformers, lines, and so on. Okay, now I am considering a single line to ground fault at this fault location F. At the fault location F, I am considering a single line to ground fault with a fault impedance of ZF. With a fault impedance of ZF, I am considering that fault. All of you getting to me? Getting? Now, tell me please, how to calculate the fault current IF? Tell me please, how to calculate this fault current IF? Simple. As we said in our analysis, first we should construct positive sequence network with respect to fault location, Thevenin network. Negative sequence Thevenin network with respect to fault location. Zero sequence Thevenin network with respect to fault location. Then we should connect them in series. Across that series combination, we should keep 3 ZF. That is the 3 times of fault impedance. After doing that, find out sequence current and multiply that with 3. That is nothing but the fault current. Getting me? So fault current IF is nothing but fault current IF is nothing but 3 times of the zero sequence current. So I can write this like 3 times of zero sequence current means, first of all, with respect to fault location, pre-fault voltage is VPF. VPF is a pre-fault voltage with respect to fault location. It may not be equals to 1 per unit. It may not be equals to 1 per unit. Sometimes operating voltage may be less than the rated voltage, or operating voltage may be more than the rated voltage. In that perspective, we can't say that always a pre-fault voltage equals to 1 per unit. Sometimes it may be less than 1, sometimes it may be more than 1 also. Okay. And as usual, with respect to fault location, we have to find out positive sequence Thevenin impedance, Z1 equivalent positive sequence Thevenin impedance, Z2 equivalent negative sequence Thevenin impedance, Z0 equivalent zero sequence Thevenin impedance. These are sequence impedances. Sequence Thevenin impedances. Thevenin impedances. Thevenin impedances. Z1 equivalent, Z2 equivalent, and then Z0 equivalent. Okay. So after calculating these sequence Thevenin impedances along with the pre-fault voltage, simply I will write that fault current IF as, I am going to say fault current IF as 3 times of pre-fault voltage VPF by positive sequence Thevenin impedance plus negative sequence Thevenin impedance plus zero sequence Thevenin impedance plus 3 times of the fault impedance ZF. See, don't bother about the value of 3 times of ZF. Don't bother about the value of 3 times of ZF. If you have that type of number, that is already involved in the Z0 equivalent. If there is something like 3 times of ZF, 3 times of neutral impedances of your network, that will be obviously involved in the Z0 equivalent calculation. Okay, so this is a generalized fault current expression for single line to ground fault for fault at any place in the system. Any place in the system. All of you clear about this generalization? Anybody having a doubt? Please tell me, please. Please tell me at this point. Does anybody have a doubt regarding this generalization? All of you clear? And that's what I am saying, Anupur. Till now, I said the same thing. Why not Zn, sir? Again, you are asking me. That Zn may be involved in the Z0 equivalent, I am saying. The Zn value might be involved in the Z0 equivalent. Okay. You wrote again, where I have written 3 ZF? I have written 3 ZF. Please look and talk. 3 times of ZF, fault impedance ZF. Okay, fine. Next thing. We will solve many number of questions. Can you observe? See, generalization means it's a very simple thing. Just look here. Wherever you have a short circuit fault, so-called single line to ground fault, with respect to that fault location, you calculate the pre-fault voltage. Okay, you calculate Z1 equivalent, positive sequence Thevenin impedance. Means you should replace each and every equipment with its positive sequence equivalent model, and you find out Thevenin impedance with respect to F, which we have done in the sequence network analysis. Similarly, negative sequence network you draw, find out Thevenin impedance. Zero sequence network you draw, find out Thevenin impedance. After calculating the sequence Thevenin impedances, simply you construct the 3 sequence networks, connect them in series, and across that you keep 3 times of ZF. 3 times of ZF. And then you find out the current circulating in that loop that will give you symmetrical component of current. Multiply that with 3, that is a fault current what we are seeing. So 3 times of pre-fault voltage by Z1 equivalent plus Z2 equivalent plus Z0 equivalent plus 3 times of ZF. Okay, next thing. So we have some confusion now. I am introducing the confusion. Just try to understand. Look here. For example, yeah. Yeah, kindly look this one. For example, this is one system I have, three-phase system, one. And this is another system, again I will say three-phase system number 2. Two systems I have. System 1 and system 2 I have taken. System 1 and system 2. Between these two, we have 3 wires running, phase A wire, phase B wire, phase C wire. Let me show. Phase A wire, phase B wire, I am showing. And this is a phase C wire. Like this, we have 3 wires. Phase A, phase B, phase C wires. Very, very simple question. Very, very simple question. I had a phase A to ground fault, something like this. Phase A to ground fault, LG fault, we have something like that. After that, LG fault has been occurred. After that, LG fault has been occurred at this place. Definitely, this side of A will carry some current. This side of A will carry some current. So you can call it is IA A1 if you write, you get it out. IA of 1, better from one side. You get some current from the side as IA of 2. After getting that IA of 1 and IA of 2, that summation will give you fault current IA. IA of 1 current plus IA of 2 current, that summation is a fault current IF I am showing. Phase A wire is carrying the current. What about current in the phase B wire? What about current in the phase C wire? That's the question. In this system particularly, where we have some system on one side consisting number of generators, transformer lines. On other side, we have system 2 consisting number of generators, transformers, transmission lines. Okay. So now if I have a short circuit fault at this place, some current is supplied by system 1 to the fault in the phase A. Some current is supplied by system 2 into the fault. What about the currents in B and C? That's the question. What about the currents in B and C? May or may not be 0. We don't know, because B is experiencing a closed circuit and C is also experiencing a closed circuit. But in the earlier case, we have taken only one generator. We have taken only one generator, and by the generator, it is clearly visualized to be as B is open, C is also open. But here, I don't know about the B. B might be closed, C might be closed, and there might be some current which we don't know, right? We don't know. Yes or no? Yeah. Please tell me, all of you. B current I don't know, and C current also I don't know, and these values may not be equals to 0. May not be equals to 0. May not be equals to 0. But you see, whatever the thing you have done, particularly with symmetrical components, we have taken up IA as a fault current. But B and C currents we have taken 0. By taking the B and C currents as 0, we ended up with a conclusion that IA0 equals to IA1 equals to IA2. Yes or no? We ended up with a conclusion that IA0 equals to IA1 equals to IA2 by saying that B and C currents are equals to 0. But practically speaking, in this type of system, B and C currents are non-zero, right? B and C currents are non-zero. Means can we do this, what we call fault analysis with the help of symmetrical components, as we said earlier? Can we do this fault analysis similar to the previous one? Anybody? Similar to the previous one? No, we can't do. Okay. But what I am going to tell is, I will use the same methodology of the previous one. By making some small modification in this circuit, which is a perfect and valid modification. Okay, I'm going to redraw this. System, something like this. Just observe here. System number 1. This is system number 2. And this is a phase A line. It's a original line, or you can say practical line, better. Original line, or you can say practical line, AVC. Like this I have taken. Original line. Whatever the line you see on the tower, that I have drawn here on the paper. Now, To make my, listen, to make my analysis simple by using symmetrical components to find out fault current. So I am taking on the paper, not practically outside on the line, not practically outside on the line, on the paper, I am taking one tapping of conductor A like this, tapping of conductor B like this, tapping of conductor C like this. I am asking you same question. I am asking you same question. This is my fault location. This is my fault location. Do you have these types of tappings at the fault location on practical line? Do you have these tappings on the practical transmission line at the fault location? Do you have it or not? No, we don't have it. We don't have it. That we have drawn only on the paper for analysis. Now, listen here. Now, I will take phase A to ground fault simply on this. I've taken phase A to ground fault. So, this is a phase A current which I am saying now, that is a fault current also. Phase A current or I say fault current also. What is phase B outcoming current? Anybody? What is phase C outcoming current? Tell me please. What is phase A outgoing current and phase B outgoing current? Zeros. Zero, yes or no? This phase B outgoing current will be zero. Else I will show you. IB equals 0. And phase C outgoing current is also equal 0. Now you have that type of same relation, right? IA equals to fault current. B current is 0. C current is 0. And then you can say IA0 equals to IA1 equals to IA2. We can find out this fault current easily from these relations. Yes or no? Okay, fine. Now, if you look into the practical transmission line wires here, you look into the practical transmission line wires, this phase A will carry some current of IA1 from this side, IA of 2 from this side, and summation of the two is a fault current, which is a phase A current I am feeling. Phase A current of fault, phase A current of fault element, phase A current of the fault element. Now, this B might be carrying some current, I don't know about it. And that current is simply flowing in this line only, and that's not coming out. So that phase B of the fault current, phase B component of the fault current equals to 0, but line current may exist. Line current may exist. Similarly, phase C component of the fault current equals to 0, but some line current may exist. All of you getting my words? Yeah. How it is 0 means it's open, right, Spandana? Since open, IB equals 0, that's it. Outgoing current equals 0, but in the line we have some current. In the line, B line we have some current. C line also we have some current. But outgoing current will be equals to 0. That's what I am saying. Okay? Impedance of the tappings will be 0. Impedance of that impedance tappings you are drawing on the paper, right? Yeah, I think all of you getting this one. So now I am going to say this is, yeah, I will redraw the models in the same way for everything further. Okay. But listen here. Any time if somebody asks you, Mohammed, I will come to you now. Just listen. If somebody asks you in some interview, for single line to ground fault, on phase A conductor, which phase will carry the current? Which phase will carry the current? You say simply phase A will carry the current, sir. And if they have asked one more question as a written to you, what about phase B and phase C currents? Then you say, sir, if the fault is at the end of the line, and if you don't have any other system further, means if you have one system something like this, sir. If you have some system something like this, sir, and if I take fault on the phase A conductor, only A will carry the current, sir. B current and C currents will be 0. But if you have one more system on the other side, sir, like this. If you have one more system on the other side, this phase A will carry the current. B and C currents may also exist. B and C currents may also exist. That you should answer. Then how you do fault analysis? How you do fault analysis means, as a theoretical study, I am taking some tappings from phase A conductor, phase B conductor, phase C conductor, and I will take fault on the phase A conductor side, and current flowing into the fault elements I am considering in the analysis. Current flowing into the fault elements means phase A is carrying the fault current, phase B of the fault element is 0, phase C current in the fault element equals to 0. So this is a modeling of the fault element. It is a modeling of the fault element. Okay, so I'll say this is modeling of the fault element. Modeling of fault element. Fault element. Yeah, so I think many of you might be clear with this concept what is said now. Okay, next immediately I'll take up one something called a short circuit MVA calculation or fault level calculation, right? At the same level. Then we will think about the breaker rating, as I said earlier. Next slide, I'm taking up fault level calculation, or you say short circuit MVA calculation. Fault level or short circuit MVA, 3-phase. Or short circuit capacity, single line to ground fault, short circuit capacity. Yeah, check this one. What is fault level formula in MVA? Fault level formula in terms of MVA. We have written some formula earlier. In the yesterday class, we have written that I am repeating now. Pre-fault voltage per unit value, fault current magnitude per unit value, S base 3-phase, base MVA 3-phase. Pre-fault voltage per unit value, fault current per unit value, multiplied with S base 3-phase. Simply that fault current per unit formula you have that you dump here. Okay, so it will come pre-fault voltage per unit multiplied with what fault current equation I will take? I'll take generalized current equation. Generalized fault current equation I am considering. What is the generalized fault current equation? 3 into pre-fault voltage. 3 into pre-fault voltage per unit. All the things I am writing in per unit only. By Z1 equivalent plus Z2 equivalent plus Z0 equivalent is magnitude per unit into S base 3-phase. S base 3-phase. I think you are comfortable with this. Okay, so VPF per unit and 3 VPF. This VPF is also in the per unit domain. So you get VPF square. VPF per unit square. So it is 3 into pre-fault voltage per unit number square by magnitude Z1 equivalent plus Z2 equivalent plus Z0 equivalent in per unit form multiplied to S base 3-phase. S base 3-phase. Okay, I think all of you getting this one. Okay, if you have that 3ZF, that also you can consider. I will add. Good. I will add 3ZF also. After that, I will make assumptions. You add 3ZF also. Good. 3ZF also in the formula. Okay, next. See, I'm making one assumption that ZF value is equal to 0. By making that ZF value equals 0, you will get 3 into pre-fault voltage square by Z1 plus Z2 plus Z0 magnitude in per unit into S base 3-phase. And I will make some more assumptions to have some modification for this equation. Pre-fault voltage I will assume as 1 per unit. Okay, and network is resistance free, means there is no loss in the network. So the Z1 equivalent I will replace with JX1 equivalent, Z2 equivalent I will replace with JX2 equivalent, Z0 equivalent will be JX0 equivalent. Like that I will replace the terms. Step by step I will go. Let ZF is equals to 0 and pre-fault voltage magnitude is equals to 1 per unit. Pre-fault voltage equals to rated voltage. That's the thing I am saying. So I can write from this fault level in MVA, fault level in terms of MVA is equals to 3 into S base 3-phase value in the numerator Denominator, you will get magnitude Z1 plus Z2 plus Z0 in per unit form. 3 times of S base 3 phase value by Z1 equivalent plus Z2 equivalent plus Z0 equivalent in per unit form. Okay, now next I'll say let the network is lossless. Network is lossless. By making that, you write this fault level in MVA, same equation we are writing now, 3 into S base 3 phase value, S base 3 phase value by Jx1 equivalent plus Jx2 equivalent plus Jx0 equivalent magnitude. Okay, so that magnitude is nothing but simply x1 plus x2 plus x0 in per unit form. X1 equivalent plus x2 equivalent plus x0 equivalent in per unit form. And numerator we have 3 into S base 3. So finally, an approximate formula, it's not exact one. After making many assumptions, can get this fault level value in terms of MVA as 3 into S base 3 phase number by x1 equivalent plus x2 equivalent plus x0 equivalent in per unit domain. X1 equivalent plus x2 equivalent plus x0 equivalent in per unit domain. Okay, it's an approximate formula only. It's an approximate formula only. Anywhere you get a doubt, what formula I have to use for the fault level? What formula I have to use for fault level? Use this equation only. Use this equation. Fault level in terms of MVA is equals to default voltage in per unit multiplied with fault current in per unit multiplied with S base 3 phase. You use this equation only. It is valid for all cases without making any assumptions. By making the assumptions, what I said, you can take this formula also. Okay. Next one. So I'm showing previous slide. Somebody asked me to show previous slide. So why we consider impedance as reactance? That's what we assumed as Mohana. We assumed that resistance is 0 in the network. Lossless network we assume. So we don't have resistances. Only reactances will exist in the network. That's the assumption. Okay, next thing. So I will be going for selection of circuit breaker rating based on this LG fault analysis. Okay, so I'll take in the next slide. CB rating selection. Circuit breaker rating selection based on LG fault. Based on single line to ground fault. Single line to ground fault. Yeah, present. So, see, this is one alternator I am showing you. Like this. Generally, the breaker what we have in the system is of 3-phase breaker type. Generally, whatever the breaker we have in the system, that's a 3-phase breaker type. So star connect alternator with some grounding neutral. Okay, look here. For time being, I'm going to discuss this issue with respect to single pole breakers. With respect to single pole breakers, I'm going to discuss this one. By taking up that, we convert that into 3-pole breaker or 3-phase breaker capacity. Yeah, look. This is a single pole breaker in the phase A conductor, single pole breaker in the phase B conductor, similarly single pole breaker in the phase C conductor, Look once. I had a short circuit fault on this conductor A. conductor A to ground, we have a short circuit fault, and it's carrying some current as IF, and the line will carry same amount of current IA. Line will carry same amount of current IA. I'm asking you very, very simple question here. I'm asking you very, very simple question. I have discussed this one earlier also. What current the breaker is interrupting? What current the breaker has to interrupt? Is it fault current or phase current? Or line current? Anything. Phase current, line current, both are same terms only. I am repeating the question. What current the breaker has to interrupt? Is it fault current or phase current? Which current it has to interrupt? Phase current, not the fault current. Where you are keeping the breaker? On the transmission line or on the phase of the transmission line. Okay, so this breaker has to interrupt a current of IA. This breaker has to interrupt a current of IA. What is the rating of this breaker? How much MVA? How much MVA power it has to interrupt? Magnitude, apparent. How much apparent power it has to interrupt? Means simply phase voltage magnitude multiplied with that IA current. Okay, so I can write circuit breaker A rating. CBA rating is nothing but simply phase voltage magnitude into phase A current here. Phase magnitude voltage into phase A current. Next thing. It may be in this case, it may not be in all cases, right? Vedanta. May not be in all cases, right? Next one. See, what is the breaker B rating I have to select now? What is the rating of the breaker B I have to select? Can I select this number 0? Can I select the breaker B rating as 0? No. You should not select. What's wrong if you are saying I have just go through the previous classes which I discussed, Aishwarya? If you have one more supply from this side, can you say IF is a current which is interrupting the breaker? Yeah, kindly listen to me. What is breaker B current? Breaker B current. That is 0 in this case. That is 0 in this case. Is it the meaning to say we can design the breaker? We can design the circuit breaker B with 0? No. See, by feeling that, if I have fault on phase B, we are studying that we have a phase A to ground fault, but we are not sure that always we get phase A to ground fault, right? We may get fault from phase B to ground also. So if you have a fault from phase B to ground, how much is an IB current? How much is the IB current? That will be same as the magnitude of the IA current, what we are doing now. I don't know whether you have understood the statement or not. If you want me to repeat, I will repeat it. Please tell me. Can I repeat again? Yeah, listen here. Phase A, we have taken fault, we got some current IA. Similarly, we have to take phase B to ground fault. By removing this one, you should take phase B to ground fault. Then how much is this IB current? That will come same as the IA current, what you have calculated earlier. For example, for phase A to ground fault, if we get the phase A current as 5 per unit. Phase A to ground fault, you got the phase A current as 5 per unit. Now, if you take fault from phase B to ground, you will get that magnitude again as 5 only. What is the reason means impedance network is not changing now. Per phase impedances will be remain same for the phase A as well as the phase B. That's the reason. Similarly, rather than phase B to ground, if you have phase C to ground fault, then again the magnitude of that current will be same as that 5 per unit current what you said. I think now you are clear. Yeah. Now tell me. Circuit breaker A has to be designed with this much amount of rating. What about breaker B? How much rating? Same rating. Breaker C, same rating. Then what is the 3-phase breaker rating I should consider now? 3 into V phase into that IA current we have to consider. I think it's clear now. So, CB rating 3-phase value, circuit breaker rating 3-phase value will be 3 into phase voltage into phase A current magnitude. It will be in kilovolts, it will be in kiloamps. If you want to write these numbers in per unit, earlier also we have written the same. 3 into phase voltage per unit number, generally 1 per unit, phase A current per unit number, multiplied with S base 3 phase, sorry, S base per phase. And 3 into S base per phase, you can write it as S base 3 phase also. You can write this as S base 3 phase. Phase voltage per unit value multiplied with phase A current per unit value multiplied with S base 3 phase. Already you know IA per unit. What's the IA per unit formula? That is nothing but fault current in this case, so that you can use the fault current formula only here also. But if the current is coming from other side, if the current is coming from the other side also, then this IA and IF may not be equal. At that time, you have to do some sort of current division and you have to calculate the current IA. Okay, yeah. So I'll write for the system taken, phase A current and fault currents are equal. Phase A current and fault currents are equal. So I can write now from this CV rating, three phase is equals to phase voltage per unit, phase A current, pre-fault voltage by 3 times by only magnitude we need now. So modulus. You can write Z1 equivalent plus Z2 equivalent plus Z0 equivalent plus 3 times of ZF. Multiply to S base 3 phase. And this current shall be taken in the per unit domain. This current shall be taken in the per unit domain. And if you want, you can extend it further, else you can leave it. No issue. Okay. Circuit breaker rating selection based on the 3-phase short circuit fault. Sorry, single line to ground fault. Single line to ground fault. Next, we will take up some problems on this single line to ground fault further. Single line to ground fault. Yeah. So I'm taking the first problem here. Moderate. So in the questions file, what we have uploaded. 6th question I am taking up. 6th one. Yeah. Go through this question. So a 3-phase synchronous generator, with armature resistance value RA equals to 0.1 per unit. And sequence reactances are given as XD double dash 0.2 per unit, X2 0.2 per unit, X0 0.1 per unit. Start value 0.1 per unit. The alternator neutral is grounded through a reactance of 0.03 per unit. The single line to ground fault current magnitude at the alternator terminals is dash per unit. Single line to ground fault current magnitude in per unit is how much? Yeah, all the things we are discussing only for no load operation. Yeah, anybody? Just take up this problem first. We have an alternator like this, 3-phase alternator, and you give the armature resistance value of this one, RA 0.1 per unit. XD double dash value itself is X1, right? XD double dash value, what they have given itself is a value of X1. X1 is nothing but XD double dash number. Point. Negative sequence reactance number he said 0.2. Zero sequence reactance number he said as 0.1. All are in per unit. All are in per unit. And this alternator neutral is grounded through a reactance of 0.03. Alternator neutral is grounded through a reactance of 0.03. Now, the single line to ground fault current magnitude at the alternator terminals is how much? So I am taking the single line to ground fault at alternator terminals means which terminal is said? Is it phase A, phase B, phase C? Nothing mentioned. You take on phase A to ground. Phase A to ground, you take, and you find out that fault current is IF. Okay, see, if you want, you draw the sequence network connection as we have done earlier, else you write the formula directly, substitute the numbers. Okay, yeah. See, first of all, we see if he is asking fault current in the examination, we have to calculate only subtransient fault current. He is asking fault current in the examination, we should give the answer only as a subtransient fault current. Yeah, let's take that single line to ground fault current, IF. So 3 times of pre-fault voltage value I by positive sequence impedance of the alternator Z1, negative sequence impedance of the alternator Z2, zero sequence impedance of alternator Z0. We have Zn also in the alternator, right? So we should keep this one place 3 times of Zn. And is there any fault impedance mentioned in the problem? Anything mentioned regarding fault impedance? No. So you don't need to bother with the fault impedance. Okay. What will be the value of Z1 here? What will be the value of Z1? Anybody please tell me? Yeah, XD dash, XD also positive sequence impedance only, right? All the three, XD double dash, XD dash. In the alternator short circuit we studied, na? XD double dash, XD dash, XD. All the three are positive sequence impedance only. According to state of operation, we have to consider any one of these 3 numbers. Okay, negative sequence impedance is different number. Reactance X2. Zero sequence reactance is a different number, that is X0. Okay, what is Z1 here? What is Z1 we have to write? It is RA plus JX1. Resistance is given, right? See, whatever the armature resistance is said in the problem 0.1 per unit, it will exist in the positive sequence network, in the negative sequence network, as well as in the zero sequence network also. Okay, so according to that, we should take up the values of Z1, Z0. Z1 is that. What is Z2 number? RA plus JX2. What is Z0 number? RA plus JX0. Zn number is JXM. XM. Okay, so it is 0.1 plus J.2 per unit. It is again 0.1 plus J.2 per unit. And R0, sorry, RA plus X0, 0.1 plus J.2. 0.1 plus J.1 per unit. And this Xn value how much? 0.03 means it is J0.03. And you dump all the values in this. What is pre-fault voltage given in the problem? How much is pre-fault voltage given in the problem? It didn't mention anything. So you take that VPF as 1 per unit. Anything mentioned? No. So let pre-fault voltage is equals to 1 at an angle 0 degree per unit. 1 at an angle 0 degree per unit. Now you write down that LG fault current formula. LG fault current formula 3 into pre-fault voltage by Z1 plus Z2, 0.1 plus J0.2, Z1 plus Z2, 0.1 plus J0.2 plus Z0. What is the value of Z0? 0.1 plus J.1, 0.1 plus J.1 plus 3 times of Zn. 3 times of Zn means that is J0.09. J0.09. So this will come to be 3 by total resistance number is 0.3 plus J. It is 0.5 and 0.5. J0.5. See, he is asking only magnitude of the current. Asking only magnitude of current. which is numerator magnitude 3 by denominator magnitude will be 0.3 square plus 0.59 square. 0.59 square in per unit form. Now, you please get this number how much? 4.532 per unit. 4.532 per unit. 4.532 per unit. That is a fault current magnitude for LG fault at the terminals of the alternator. Very simple problem. Very simple problem. Next. So I will display one more problem to you. 151 slide. It's a question slide. I already shared this file to you. Question slide. Let's take one more problem here. Go through this question. Make it quick, please. Yeah. So a three-phase synchronous generator has sequence reactances x1 0.2, x2 0.3 per unit, and x0 0.1 per unit. The alternator neutral is grounded through a reactance of xn equals to 0.05 per unit. If an arcing fault means flashover fault, insulation flashover fault, occurs from phase A to ground, at an operating voltage of 1.4 per unit. Means what is that 1.4 given in the data? What is that 1.4 per unit given in the data? What is 1.4? That's a pre-fault voltage. That's a pre-fault voltage value. Okay. The fault impedance is ZF equals to 0.2 per unit. Fault impedance ZF equals to 0.2 per unit. What is the nature of this impedance now? According to the data given, impedance is 0.2, he said now. Impedance is 0.2 means, is it a resistance or reactance for you? Is it a resistance or reactance for you? We should consider that as resistance value. Following all of you, this 0.2 per unit is a resistance. Okay. The value of arcing fault current is dash per unit time. Very simple question, direct question only again. So I can say in the solution, this is alternator we are having. And this star neutral is grounded with reactance of xn. Okay, let's write the data quickly. x1 0.2 per unit, x2 0.3 per unit, zero sequence reactance x0 0.1 per unit, neutral reactance 0.05 per unit, pre-fault voltage 1.4, fault impedance nothing but fault resistance here 0.2. Okay, now fault current formula IF LG fault IF equals to 3 into pre-fault voltage value by Z1 plus Z2 plus Z0 plus 3Zn. 3Zn also there in the question, plus 3 times of the fault impedance. Fault impedance is also there. Okay. Now you can keep these numbers. 3 into pre-fault voltage 1.4. You assume that as a reference. By what is Z1? JX1. Z1 is what? JX1 means J0.2. Okay. What is Z2 we have to take? J0.3. What is Z0? Z0 will be J0.1 plus 3 times of Zn in the sense J0.15. J0.15 and 3 times of ZF. 3 times of ZF in the sense you get this number as 0.6. That's the resistor. ZF is in the form of resistance. Okay, you can it will be 5.2 in the numerator. 4. 4.2 in the numerator. Denominator, real part is 0.6 and J, imaginary part is 0.5, 0.6, 0.75. 0.75. And you take that magnitude of current, what is required for us. Magnitude of current, IF magnitude. Numerator, it is 4.2. Denominator, we have square root of 75 square. 0.6 square plus 0.75 square in per unit form. Get this magnitude how much? How much is this magnitude? It is 4.372 per unit. 4.372 per unit. Getting? 4.372 per unit. Sir, in previous sum, does armature resistance will present in all cylindrical components? Why so in zero sequence would not? In all we have considered 3D, just you go through that. I have considered the armature resistance in all cases. In all positive, negative, and zero sequence networks, we have considered that armature resistance value. Okay. Zn is at reactance, right? Zn is said in the nature of reactance. You see this statement. Reactance of Xn equals to 0.05. If you want, you can, in the problem, if we said there's a resistive grounding, we have to follow resistance value. If they have given, we will consider it. Okay, anyhow, have a break for 15 minutes. After break, we will continue with one more problem in the single line to ground fault. 15 minutes break. 15 minutes. Okay. Yeah. So I have resumed audio video on screen. So the next question I am giving here. Right. Next question. A three-phase synchronous generator rated for 22 kV, 50 MVA. Three-phase synchronous generator rated for 22 kV, 50 MVA has the sequence reactances X1 equals to X2 0.25 per unit and X0 0.05 per unit. The alternator is operating at no load condition with pre-fault terminal voltages as VA 1.1 at an angle 0 degree, VB 1.1 at an angle minus 120 degree, VC 1.1 at an angle plus 120 degree in the per unit form. A single line to ground fault occurs on the phase B at this operating condition. It will give the fault current as dash kiloamperes. In bracket, alternator neutral is solidly grounded. Alternator neutral is solidly grounded. Okay, yeah. So just you go through the data what they have given here in the question. So this is an alternator, three-phase alternator. Okay, yeah. So it is 22 kV, 50 MVA rating. So 22 kV, it's obviously line-to-line voltage rating of the alternator. 50 MVA, it is of a three-phase MVA rating of the alternator. 50 MVA is a three-phase MVA rating. Next, sequence reactances he mentioned. X1 value, X2 value, both are equal. 0.25 per unit. And X0 value, how much? 0.05 per unit. 0.05 per unit. Okay, next, any other data? He didn't mention about grounding of alternator in the problem. He didn't mention about the grounding of alternator in the problem. So if he didn't mention it, we assume that it's solidly grounded. Okay, so assuming that alternator neutral is solidly grounded. Assuming that alternator neutral is solidly grounded. Assume that neutral is solidly grounded. Neutral is solidly grounded. Okay, now he's saying the terminal voltage of the alternator before occurrence of fault. Of course, it is at no load, he said, that's okay. Pre-fault terminal voltages are VA 1.1 at an angle 0, VB, VC values are given. But actually, pre-fault voltages in the alternator are pre-fault voltages in the system. We are taking with a notation of E. We are taking with a notation of E, but he said here VA, VB, VC. So what I will say here is pre-fault voltages without changing our terminology. I am writing EA 1.1 at an angle 0 degree, EB 1.1 at an angle minus 120 degree, EC 1.1 at an angle plus 120 degree. All of you getting these words, what I am saying you? Did he mention about grounding? Okay, bracket, in bracket, he said at the end. Okay, good. It is not needed now. Okay, so he mentioned that in bracket. Now, if he is not mentioning in the exam, you have to assume it as solidly grounded. Yeah, so these are the pre-fault voltages. Next thing. Single line to ground fault on phase B. Means you have phase B to ground fault, something like this. Phase B to ground fault, something like this. Then, how to draw sequence networks here? Till now, in the earlier problems, we have discussed about phase A to ground fault, where we said positive sequence network of phase A, phase B, phase C. Positive sequence network of phase A, negative sequence network of phase A, zero sequence network of phase A are connected in series. Across that, we kept a short circuit. But now the fault is on phase B. So now we are going to get positive sequence network of phase B, negative sequence network of phase B, zero sequence network of phase B connected in series. Across that, we have to keep the short circuit. Okay, so in the next slide, I will show that the single line diagram. See this. Sequence networks connection for phase B to ground fault. Sequence networks connection for phase B to ground fault. Phase B to ground fault. Yeah, simple. Positive sequence network. Like this, you have positive sequence network Z1, and this terminal voltage is a positive sequence terminal voltage VB1, and current here is IB1. We should write all the terms in terms of B. All the terms of voltage and currents you should keep in terms of B. That's it. And it's a pre-fault voltage of phase B. Pre-fault voltage of the phase B. Next one. Negative sequence voltage, so negative sequence network of phase B. If you look in this way, plus minus VB2, current here is IB. Similarly for zero sequence network, up to neutral Z0, neutral to ground as it is zero impedance given, should show short circuit. And this is plus minus VB0, and this current I am showing as IB0. Okay, now we have to add these three sequence networks in series, and across this we should keep a short circuit like this. Across this we should keep that short circuit. Okay, now what is asking us to find? What is asking us to find? Can you observe? What is the fault current value? Fault current is nothing but phase B current only. Fault current is nothing but the phase B current only. And what is phase B current now? 3 into IB1 or 3 into IB2 or 3 into IB0. Okay, now that will come to be 3 into pre-fault voltage EB1 by Z1 plus Z2 plus Z0. Of course, 3Zn is 0, 3Zf is also equals to 0. What is EB1 value? Anybody? Anybody please tell me what is EB1 value? EB1. EB1 is nothing but EB itself, right? Because all the three are, the pre-fault voltages are balanced. If you convert them into symmetrical components, you get only positive sequence component. EA1, EB1, EC1, you get. So EB1 value 1.1 at an angle minus 120 degree, we have to substitute. So let's say fault current IF is equals to 3 into EB1 is 1.1 at an angle minus 120 degrees. What is Z1? How much is Z1 in the data? J0.25, Z2, J0.25, Z0, J0.05. Substitute J0.25 plus J0.25 plus J0.05. So if you rewrite this, you'll get like 3.3 at an angle of minus 120 degree by it is 0.55 magnitude, and angle will be plus 90 degrees. Okay, so what is a 3.3 by 0.55? Anybody calculated this number in per unit? Anybody? Please tell me, calculated this number in per unit? So this magnitude is coming like 6. Okay, 6. 6 at an angle, how much? Minus 120, minus 90. So it will be minus 210 degree in per unit form. But in what units he is asking the answer? In absolute, right? He is asking in kiloamperes. Kiloamperes means this current you should multiply with the base current. Okay, so now we will find out the base current by using our regular formula. I base equals to S base 3 phase value by root 3 base. So root 3 into V base line. Root 3 into voltage base line to line. What is S base 3 phase number? Check that. 50 mega. Okay, by root 3 into V base line to line is 22 kilo. It will be in amperes. After getting this number, that you substitute, that you multiply with IF, you get that value in kiloamperes or amperes, whatever it is. So IF in terms of amperes will be 6 at an angle minus 210 degree per unit current, per unit fault current. This multiplied with How much is the base current? Anybody? Base current is how much? Base current. 1.312 kA. 1.312 kiloamperes is a base current is at 1.312 kiloamperes. That will substitute now. So this multiplied with 1.312 kiloamperes. How much is this number? 6 into 1.312. 6 into 1.312 is 7.87. 7.87 at an angle of minus 210 degree in terms of kiloamperes. That is a phase B fault current. That's a phase B fault current. Okay. You please check in your options. Do you have the type of option? 7.87 at an angle minus 210 degree. Do you have that option? After fault, internal EMFs will be remain same. Arvind. After fault, internal EMFs will be remain same. Only terminal voltages are going to be changed. Tell me please. How much is this number? Which option is correct? See, actually, we got minus 210 degree in that angle. So 7.87, 3 options are there. One option with plus 210, next option with minus 90, next option with plus 150. So this minus 210 degree, we can replace with minus 210 degree plus 360. Minus 210 degree plus 360 degree, like that you can replace. So this will come to be 7.87 at an angle of 150 degree in terms of kiloamperes. 7.87 at an angle of plus 150 degree in terms of kiloamperes. And what's the correct option here? Option C is a correct one. Is it so? Yeah. Option C is a correct one. So that angle is also very, very important in this. Angle is also very, very important in this. Okay. Next one. Next problem I'm going to take up in the single line to ground fault. Single line to ground fault. Yeah, so I'm moving ahead. Next question. It was a very, very simple question what I'm giving you. Consider the following single line diagram. Following single line diagram. See this? Generator, transformer, line, transmission line. Okay, next thing. It is a star, is a delta star ground. Okay, for generator, x1 equals to x2, 0.1 per unit. Transformer, x1 equals to x2 equal to x0, 0.1 per unit. Line, x1 equals to x2, 0.1, x0 equals to 0.3 per unit. Simple, very simple question. For a single line to ground fault, at midpoint of transmission line, at no load operation, the ground current will be dash per unit. In bracket you write magnitude. Ground current will be dash per unit. You write in bracket magnitude. Yeah. Some of the problems are gate problems only, Dinesh, what I am discussing. Models, gate problem models. Okay, you please go through this question once. Go through this question and try to tell the answer. It's a very simple question only, not laborious also. If you have good idea, you can say this answer in very few steps itself. Okay. But as we are in the learning stage, let's say. First, he said single line to ground fault at midpoint of transmission line wire at no load operation. The ground current will be how much? That's the question, right? So first we have to consider the positive sequence network of that, find out the positive sequence impedance, then negative sequence network and negative sequence impedance, zero sequence network and zero sequence impedance. After calculating that, fault current is ground current. Ground current and fault current both are same. Ground current and fault current both are same. So that you can say 3 times of default voltage by Z1 equivalent plus Z2 equivalent plus Z0 equivalent. That's it. Okay. Simple question. Yeah. So first, positive sequence network, if you draw, positive sequence network, if you are drawing, first generator in the positive sequence network represented with a voltage source in series with the impedance. Okay. And you have transformer above this, it will be represented simply as a series impedance. After that, you have some transmission line wire, but that line you should divide into 2 parts. Line you should divide into 2 parts like this, and this is a neutral. This is a neutral. Okay. And what is a generator positive sequence impedance? Generator, transformer here, and this was a line. Okay, what is the generator positive sequence impedance? J0.1. This number was J0.1. Okay, what is the transformer positive sequence impedance? J0.1. And line positive sequence impedance is J0.1. That we should divide into 2 parts. Divide into 2 parts means first part is J0.05, second part will be J0.05. And we have to calculate that equivalent Thevenin impedance with respect to midpoint of transmission line wire. Midpoint of transmission line wire by killing the sources. So you can kill the source like this. By killing the source, if you look at this point, if you look at this point, what is the Z equivalent value you can get from? This side it is open. This side is open means the second value of J0.05 is not at all effective to us. Only that first number is effective. First number is effective. Moreover, you should say that equivalent impedance is 0.1 plus 0.1 plus 0.05. So with respect to the fault location, so-called midpoint of line, Z1 equivalent, if you write, it will come to be J.1 plus J.1 plus J0.05. So this number is J0.25 per unit. J0.25 per unit. Like that you can see. How much is the negative sequence impedance? How much is the negative sequence Thevenin impedance to be expected? Will it be equal to the same number? Z2 equivalent. Can I say it is same as Z1 equivalent? Yes. Why? All the apparatus are having X1 and X2 values as equal. So that Z2 equivalent with respect to fault location will be same number. Okay. So with respect to fault location, negative sequence Thevenin impedance value, if you calculate, it will be same as positive sequence Thevenin impedance. And this you can write as J0.25 in per unit form. And you have to draw zero sequence network and you have to find out the zero sequence Thevenin impedance. Simple. So zero sequence network, if you draw zero sequence network, first of all, we have a generator with Y connection. Neutral is ungrounded. Y connection, neutral is ungrounded. Okay. So this is generator. Up to neutral, we should keep its zero sequence impedance. Neutral to ground, we should show 3 times of Zn. 3 times of Zn means it is open circuit infinite. Open circuit, that will be infinite. Okay. And how much is the zero sequence impedance of generator given in the data? Nothing mentioned. Zero sequence reactance of generator value not given. Maybe it is not needed. Maybe it is not needed in the solution. Okay, fine. So next you have a transformer. I'll show primary and secondary here for transformer. Primary and secondary for this transformer. So I will show first impedance diagram, open diagram. And zero sequence impedance of transformer is J0.1. J0.1. What is the primary connection? Delta. Delta means what? Shunt switch we have to close. Delta means you should close the shunt switch. What is secondary connection? Star grounded. Star grounded means We should close the series switch. Okay, next what we have? Next line. Line we should divide into two parts. Okay, so I show line dividing into two parts like this. So the first part will be J0.15 per unit. Second part will be again J0.15 per unit. And this is a location of fault we have. So with respect to fault location, we have to calculate that Z0 equivalent. How much is that Z0 equivalent with respect to fault location now? J0.15 plus J0.1. That number also comes to be J0.25. Okay. So with respect to fault location, if you calculate zero sequence Thevenin impedance, that is J0.1 plus J0.15, that number will be J0.25 per unit. So I think all of you getting this one. Okay, now ground current, or you say fault current value. Ground current is nothing but fault current only. That is nothing but 3 times of pre-fault voltage by Z1 plus Z2 plus Z0. 3 ZF we don't have. 3 ZF we don't have. So 3 into pre-fault voltage value 1. 3 into pre-fault voltage value 1. Okay. What is Z1 equivalent, Z2 equivalent, Z0 equivalent? All are equal. So that is J0.25 plus J0.25 plus again J0.25. So I think you get this number minus J4 per unit. Okay. He might be asking only magnitude of that current. So it will be 4 per unit, which we have to give in the blank. 4 per unit current. Sir, why 3 ZF is not there? ZF value they have not given in the question, right? Fault impedance value they have not given in the question. So I have assumed that as 0. That's it. Yeah. So I'm showing 163 slide. If anybody is still writing, please complete it quickly. 163 slide. Okay. So if you have completed, let me take one more problem with respect to single line to ground fault quickly. Yeah. So taking one more problem here. It is a previous GATE examination question. Maybe with some change in the numbers. Some change in the numbers. But model is in this way. Model they have given in this manner. Go through it. So consider the following single line diagram. Consider the following single line diagram in which 2 generators are connected in parallel. G1, G2. Both generators are identical. Both generators are identical. And each one is rated for 100 MVA, 11 kV. First generator 100 MVA, 11 kV. Second generator also 100 MVA, 11 kV. Both generators are having X1, X2 equal 0.2. X0 0.05. First generator neutral was isolated from ground. First generator neutral was not connected to ground and it is isolated. Okay. And the second generator neutral is grounded through a reactance of Xn equals to 0.05. Grounded with a reactance of 0.05 per unit. For a single line to ground fault on the bus bar, the bus bar should be. And we have a single line to ground fault on the bus bar. Find the neutral voltages of both generators in kilovolts. What is the neutral voltage of the generator 1 as well as what is the neutral voltage of the generator 2? That's the question. Neutral voltages calculation they have asked. Okay. So let's say the next slide. So this is generator 1 or isolated neutral. Generator 2 star with some reactance grounding. And it was a bus bar we have mentioned. Bus bar. Let's look into the numbers again. Ratings. Ratings are 100 MVA, 11 kV. Each generator. 100 MVA means it is a three-phase rating of alternator, line to line voltage of the rated voltage. X1, X2 both are equal to 0.2 per unit. X1 and X2 both will be equals to 0.2 per unit, and X0 value 0.05. X0 value was 0.05 per unit. Okay, Xn value he said 0.05. Means all these reactances, whatever they have given, might be on the common base. All these reactances might be on the same base of 100 MVA, 11 kV. Let us consider those values itself as base numbers. So you no need to modify these reactances at all. Okay. So these values, whatever we have ratings, itself are considered as base values. Considered as base values. Considered as base values. Okay. Next. See, you have to consider the single line to ground fault, but you no need to calculate the fault current. You have to find out only neutral voltages in the both generators. Then how to approach to this problem means, first we will try to find out that current. Yeah, see this. Is so first I will take positive sequence network of this one. I will draw the positive sequence equivalent model. Negative sequence network equivalent model. Zero sequence network equivalent model. I will show that. I will show the things first. After that, we will think about the neutral voltages calculation. Okay. So let's say first positive sequence network. Positive sequence network. First generator 1 represented like this. Generator 2 in the same way represented. Okay. So now we said that x1 value j 0.1 means this number is, sorry, 0.2 or 0.1. So this number is also j 0.2. This for generator 1 and this for generator 2. Both numbers are j 0.2. Now, how much is the value of Z1 equivalent with respect to this bus bar? This is a bus bar. This is a bus bar. So with respect to this bus bar, if you calculate the Z1 equivalent value, how much you are going to get that number? So that is j 0.2 in parallel with j 0.2. This number will come to be j 0.1 per unit. Simple. That is a positive sequence Thevenin impedance. Positive sequence Thevenin impedance. How is the negative sequence Thevenin impedance? Will it come same number? Yes, because both are having same negative sequence reactance. Yes, so it will come to be same number. Okay, else for your understanding or for your information, I'll say negative sequence network here. Generator 1, generator 2. Okay, so this is j 0.2 positive sequence impedance. So negative sequence impedance of G1 and negative sequence impedance of G2 also j 0.2. Now, with respect to this bus bar, we have to find out the negative sequence Thevenin impedance. That will come to be again j 0.2 in pair with j 0.2. That number is j 0.1. J 0.1. Now, zero sequence network. There you have to consider whether the alternate is grounded or ungrounded, all these things, right? Yeah. So I'll show zero sequence network here is very important for us, of course. Zero sequence network. First, generator 1, up to neutral, zero sequence impedance of generator is j 0.05. Neutral to ground, we should keep 3 times of Zn. That 3 times of Zn is equals to infinite. 3 times of Zn, that will be equals to infinite. That's for G1. Next, G2 generator, up to neutral, you keep j 0.05. And then neutral to ground, how much impedance we should keep for this G1 generator? We should keep 3 times of Zn. 3 times of Zn is j 0.15. T times of Zn we have to keep here. So it is J0.15. J0.15. So now you take up that negative sequence Thevenin impedance with respect to this bus bar. Sorry, zero sequence Thevenin impedance with respect to that bus bar. So how much you will get that Z0 equivalent value with respect to bus bar? So this is open means this G1 generator is not at all effective to me. Only G2 generator is effective. So the overall impedance will come to be J0.05 plus J0.15. J0.05 plus J0.15. And this number will be J0.2 per unit. J0.2 per unit. Yeah. Next. Listen, please. Listen. See, after getting this Z1 equivalent, Z2 equivalent, Z0 equivalent values, after getting these numbers, anyhow, our aim is to find out neutral voltages, right? Our aim is to find out the neutral voltage. Neutral voltage in the sense, please listen to me, Neutral voltage in the sense, simply this zero sequence network, what you have drawn here, will carry zero sequence current as IR. Means if you draw sequence networks and all, positive sequence network, negative sequence network, zero sequence network. This is zero sequence network, which is going to carry a current of IR. See, whenever this circuit is carrying IR, simply you find out this neutral one voltage. This neutral voltage VN1. This neutral voltage is VN2. Already I said, I have shown earlier, whatever the neutral voltage you find in the per phase network of this zero sequence, whatever the neutral voltage you find, that's the same value of the neutral voltage of three-phase system. Yes or no? This voltage itself is our neutral voltage. So if you are capable to get this zero sequence current value, simply from zero sequence network, we can get that neutral voltage. Okay? Yeah. So in the next slide, I will show zero sequence current value. Zero sequence current value is nothing but pre-fault voltage at the bus bar by positive sequence Thevenin impedance plus negative sequence Thevenin impedance plus zero sequence Thevenin impedance. Zero sequence current is nothing but positive sequence Thevenin impedance, negative sequence Thevenin impedance plus zero sequence Thevenin impedance. What is pre-fault voltage value? 1. They have not given it. Of course, it's a rated voltage, I think, is the problem. If you are checking it. Didn't mention anything, but still, we can say it is operating at rated voltage only. Rated voltage in the sense, you can call it 180 angle 0 degree. By what is Z1 equivalent number? What is that Z1 equivalent number? That is J0.1. Z2 equivalent number is again J0.1 only. Z0 equivalent number is J0.2. So it will be J0.4. 1 by J0.4 if you do, minus J2.5 per unit. Minus J2.5 per unit. We are required to find only sequence current here, not the fault current. I'm calculating only zero sequence current here. Zero sequence current. See, if you want to write the fault current value, then I should take 3 times. If you want to write the fault current value, then only you should take that as 3 times. Else it will be simply VPF by Z1 equivalent plus Z2 equivalent plus Z0 equivalent. You got this number is minus J2.5. Now, simply you draw the zero sequence network what you have. Simply, you take this zero sequence network what we have and you take that IR current, divide the current and try to find out the neutral voltages. Okay? Yeah. So this zero sequence network I am repeating now. This zero sequence network I am repeating. Okay. This one. Zero sequence current. So this IR current what you have is minus J 2.5 per unit. IA naught current is minus J 2.5 per unit. Now you observe that whatever the voltage you can get here, that is the zero sequence voltage VA naught. Whatever the voltage you get here, that is the zero sequence voltage VA naught. So of course, one side means generator neutral is open, means this generator will not carry any zero sequence current, G1. G1 will not carry any zero sequence current. So this current will be equals to 0. And total IA naught minus J 2.5 will flow in this circuit only. Will flow in this circuit. Then how much is the neutral 2 voltage VN2? Means generator 2 neutral voltage is how much? Generator 2 neutral voltage, if you are thinking VN2, simple VN2. Of course, we need only magnitude here. We need only magnitude. But still, if you want, you can write. IA naught current is going up, bottom plus, top minus. But we need in the reverse way. So it is minus IA naught into J 0.15. Minus IA naught into J 0.15. Minus IA naught means J 2.5 we can say. And it is J 0.15. So it is 2.5 into 0.15. How much is that number? Minus 2.5 into 0.15. 0.375. 0.375 per unit. So you take only magnitude. You don't need to bother about the angle. What you have is minus symbol and all. You take only magnitude as 0.375 in the per unit form. What will be the generator 1 neutral voltage? What will be the generator 1 neutral voltage? How much is this now? We have to apply KVL. By the application of KVL, this neutral voltage VN1 is nothing but VN naught itself. This neutral voltage VN1 is nothing but the value of VN naught. Following. See, as it is open, we can't say that the voltage is 0, right? We can't say that voltage is 0. That voltage is equals to zero sequence voltage according to circuit analysis. So generator 1 neutral voltage, if I take VN1, that is nothing but zero sequence voltage only. What is zero sequence voltage now from the circuit? Minus IA naught into J 0.05 plus J 0.15. So it is minus IA naught into J 0.05 plus J 0.15. Minus IA naught means you get J 2.5 here. And this is J 0.2. So J square you get minus. The 2.5 into 0.2, I think it will be 0.5 per unit. 0.5 per unit. Okay. And you need only magnitude. So neutral 1 voltage will be 0.5 per unit. Okay, you convert these values into absolute form. Absolute form means with what base we have to multiply these numbers? Anybody? What base you have to multiply these numbers? Per phase voltage base. We have to multiply. What is the voltage base given in the problem? Line to line voltage base is 11 kV. Per phase voltage base is 11 by root 3. Okay. So VN1 in kilovolts, nothing but VN1 per unit into voltage base per phase. Right? So VN1 in per unit is 0.5. V base per phase is 11 by root 3 in terms of kilovolts. How much is this number? I think 3.175 something, 17 kilovolts. Getting this value? 3.17 kilovolts. 3.17 kilovolts. Okay. Now, what is a neutral 2? Means generator 2 neutral voltage in kilovolts. Its per unit value multiplied with again voltage base per phase we should consider. Voltage base per phase value we should consider. and this number is 0.375 into 11 by root 3 kilo. 11 by root 3 kilovolts. Get this number. How much? 2.38 kilovolts. 2.38 kilovolts. Apply KVL, Gokul Shyam. Apply KVL. There is no current flow in that reactance existing in the branch 1. There is no current flow in the reactance of branch 1. Simple network analysis only I am using, nothing more than that. Apply KVL. Apply KVL. This is the VN1 value, right? This is a VN1 value, and you don't have any current flow here. So this node and this node will have same potential, right? This node and this node will have same potential. Then obviously this VN1 number and VN0 will be equal. That's it. Very simple. KVL application. Okay. Fine. Next. Next thing. Let me elaborate this question a little bit more. I'm going to elaborate this question a little bit more. Here. See, this is a first generator I am showing. First generator, G1. And it was a second generator. I am showing this as G2. 3 wires I am showing like this. Phase A, phase B, phase C. Similarly, here also I will show 3 wires. Okay, so 1 minute, please. 1 minute. I will come back within 1 minute. So I have resumed audio video on screen. Resumed the audio video on screen. Kindly observe. So these are ABC of generator 1, ABC of generator 2. First generator, it is star with neutral ungrounded. Second one is star, neutral grounded with a reactance. See, these two alternators are connected in parallel, means both A terminals are connected together. That will be coming out as phase A. Let's show in some color. Blue I am using. A connected together, and this is terminal A coming out. That's a bus bar actually. You can feel this is a bus bar. Next, B connected together. B and B connected together, and that I am going to call as outcoming terminal as B. Outcoming terminal as B. Next, C joined together like this. And this we are going to get as outcoming terminal here. Like this we can experience ABC wires. ABC outcoming wires. Phase A wire of G1, G2 join. G1, G2 phase B join. G1, G2 phase C also join. These are the outcoming terminals A, B, C I am showing. All of you getting this one? All of you getting? Yeah, if generator 1 neutral is solidly grounded, please do that in Imtiaz. Please kindly do that, practice it and get the answer. Of course, if it is solidly grounded, neutral 1 voltage will be 0. Generator 1 neutral voltage will be 0. Generator 2 neutral voltage will not be the number what we have calculated. It will be definitely different. Okay, listen now. See, we have phase A to ground fault on the bus bar, right? Phase A to ground fault on the bus bar, like this. Phase A to ground fault on the bus bar, like this. How much is that outcoming phase A current? Anybody? How much is the outcoming phase A current? Of course, phase B current outcoming is 0. Phase C current outcoming is also 0. What is phase A current outcoming? Anybody? What is phase A current outcoming? That is nothing but fault current only. That is nothing but fault current only. 3 times of IR. 3 times of the zero sequence current. Yes or no? Right. So I'll write that. Phase A current outcoming is into the fault 3 times of zero sequence current, which is nothing but minus J 7.5 per unit. Minus J 7.5 per unit. Okay. Now, my question is, what is the current in the generator 1 phase A? IAG1 is how much? What is the generator 2 phase A current? What is the generator 1 phase A current? What is the generator 2 phase A current? Of course, summation of these two is outcoming current phase A. Outcoming phase A current. All of you getting my point? Okay, yeah. How in the sense that we have to do by network analysis only. That we have to do by network analysis only. Let me redraw the original positive, negative, and zero sequence networks. Original positive, negative, and zero sequence networks. Yeah, let's go with this one. Let's say positive sequence network first. This one. So original positive sequence network for you. Original positive sequence network. Yeah. Just have a look here. So this is the original positive sequence network. Next one. Original negative sequence network. It will come like this, I think. Just look. Original negative sequence network. J.2. This number is also J.2 only. Original negative sequence network. And original zero sequence network, if you draw, generator up to neutral, we should keep J 0.1, I think. Neutral to ground, infinite. Second generator up to neutral, J 0.1. Neutral to ground, we should keep J 0.15. J 0.1. Okay, now you have to short all these things together like this. We should short these two also. We can keep one short circuit across. Now, this is the current circulation here, minus J 2.5. IA0, IA1, IA2, all the three are equal, which is nothing but minus J 2.5 per unit. Minus J 2.5 per unit. Tell me please, tell me please. I want to find out what is a positive sequence current in the generator 1. What is a positive sequence current in the generator 2? Or negative sequence current in the generator 1. Negative sequence current in the generator 2. Zero sequence current in the generator 1. Zero sequence current in the generator 2. These are the numbers you have to calculate first. Listen to my words. Listen to my words kindly. X naught is it 0.04? Let me cross once. 0.04. Next one. Listen. By current division rule, we have to do the things. See, of course, you know, this zero sequence current in the G1 will be 0. Zero sequence current in the G1 will be 0. Total minus J 2.5, what we have, it will flow in the G2 only. Okay, and the minus J 2.5 coming out here will be divided between these two. As both impedances are equal, it will be divided into equal parts. So this will be minus J 1.25 and this will be minus J 1.25. Again, the summation minus J 2.5 will come here. Minus J 2.5 will come here. That will be again divided between these two. One thing, please listen. These two are identical circuits, right? Both are having same voltage as well as same impedance. Both are having same voltage as well as same impedance. It is expected that this minus J 2.5 might divide equally between these two again. So positive sequence current in the G1 will come minus J 2.5 by 2. Similarly for G2 also minus J 2.5 by 2. Like that, we have to calculate sequence currents in the generator 1, sequence currents in the generator 2. Then we should go for phase A current and phase A current in the generator 1 and generator 2 respectively. So I think all of you clear at this point what I said till now. Is it okay for you? If voltages are not same, we can't divide it just by this principle what I am saying you. At the time, you have to go for the conversion of voltage sources to current sources, and then you have to reach. Else by the application of KVL, KCL, you have to. Okay, sequence currents in the generator 1 I am writing. Sequence currents in generator 1. Sequence currents in the generator 1. So I'll write first generator 1 sequence currents IA1 of G1. Positive sequence current in the generator 1. That will be minus J 2.5 by 2. Because circuits are identical as we are saying already. So this is minus J 1.25. And what is the negative sequence current of G1? Again, it will be minus J 2.5 by 2. So it is minus J 1.25. Next thing. Zero sequence current of G1 generator is 0. Zero sequence current of the G1 generator, nothing but 0. All the three sequence currents we got in the G1 generator. Next, let me write in G2 generator now. Let me write in G2 generator now. Sequence currents in G2 generator. Sequence currents in G2 generator. Simple. What is the positive sequence current in the G2 generator? Positive sequence current in the G2 generator will be again minus J 1.25. according to current division principle. Negative sequence current in the G2 generator will be minus J 1.25 again. Whereas zero sequence current in the G2 generator, that will come to be minus J 1.2, sorry, minus J 2.54. Minus J 2.5 as a whole will flow in the G2 generator, negative sequence, sorry, zero sequence. These are the sequence currents in the G1, G2. Now, what is phase A current of the G1 generator? What is phase A current of G1 generator? Anybody please tell me? What is a phase A current in the G1 generator? Tell me please. Some of these three, right? Some of these three. That will be minus J 2.5. That's it. What is a phase A current in the generator G2? Some of these three. That will come to be minus J 5. Minus J 5. That's it. Following me? Very simple, na? Very simple. Current division principle we have applied and we found sequence currents in G1, G2. Now we are moving to phase A current in the generator 1. Generator 1. Phase A current. Generator 1. Phase A current. So I'll write IA of G1. Nothing but positive sequence current of G1 generator, negative sequence current of the G1 generator, zero sequence current of the G1 generator. Positive, negative and zero sequence current summation, it is minus J 2.5 per unit you will get. You have to do that summation. Next step. G2 generator phase A current. G2 generator phase A current. So IA of G2 generator, this is nothing but positive sequence current of G2 generator, negative sequence current of G2 generator, and then zero sequence current of the G2 generator. And this number will come to be minus J 5 per unit. Minus J 5 per unit. Getting? Simple. So if you look at that three-phase diagram, you look at this three-phase diagram, this is supplying a current of minus J 2.5 and this is supplying a current of minus J 5. Can you find what is the B current in the generator 1? What is the B current in the generator 2? How will be this number? Is it 0 or non-zero? What is a phase B current in the G1 generator? What is a phase B current in the G2 generator? Anybody? Anybody, can you calculate this? Is it 0 or non-zero? Calculate and check once. Calculate and check. G1 generator phase B current. G1 generator phase B current. How to get it? G1 generator phase B current. Simple. IB of G1. IB of G1. You know already symmetrical components of phase A current in G1, right? Symmetrical components of the phase A current in G1 you know already. Means you can write zero sequence current of G1 alpha square into positive sequence current of G1 alpha into negative sequence current of G1. That's it, simple. What is zero sequence current in the G1? 0. Alpha square, we keep as it is. What is positive sequence current in the G1? Positive sequence current in the G1 is minus J 1.25 plus alpha into. What is a negative sequence current in the G1? What is a negative sequence current in the G1? That is minus J 1.25. That minus J 1.25 is common. And you get alpha square plus alpha. Alpha square plus alpha means minus 1. Minus 1. So it will come to be J 1.25 per unit. It is non-zero number. Alpha square plus alpha is minus 1. Already we discussed now. 1 plus alpha square is 0. So alpha plus alpha square will come to be minus 1. If you substitute that, minus will be cancelled. It will come to be J 1.25. J 1.25. Getting? Next thing. What is the phase B current in the G2 generator? Phase B current in the G2 generator. In your expectation, this number should be opposite to this. Means that number should come as minus J1.25. Then only the resultant phase B outgoing current will come to be 0. You calculate it and check. Calculate that number and check. Okay, G2 generator, phase B current. Phase B current. G2 generator, phase B current. So IB of G2 generator, nothing but IA naught of generator 2 plus alpha square. IA1 of generator 2 plus alpha. IA2 of generator 2. Okay, what is IA naught of G2? What is IA naught of G2? IA naught of G2 is minus J2.5 plus alpha square into, and this number is minus J1.25, and the other number plus alpha minus J1.25. So if we calculate this minus J2.5 plus minus J1.25, and you have alpha plus alpha square, that is minus 1, minus 1, minus will be cancelled out. So it's minus J1.25 per unit. Minus J1.25 per unit. Getting all of you? Similarly, you attempt to calculate the phase C currents also. Phase C current in the G1 and phase C current in the G2 will exist. Okay? So this is what I said earlier also. Even though you say we have a fault on phase A, if there is a closed path for phase B, closed path for phase C, there is a chance of current flow in the phase B and the phase C also. Okay? So we have a closed path for phase A, sorry, phase B like this, and we have a closed path for the phase C also. We calculate phase C currents later. Phase C currents later. But I'm not going to what we call change these things at all. Means violation of rules we don't have at all. Just I'll tell you. Listen. If you calculate this phase C current of G1, phase C current of G1, in my view, you get this number again minus J1.25. And if you calculate the phase C current of G2, you will get this number again J1.25. J1.25. And phase B current already you get J1.25, and this number is minus J5. Clear? Now, whatever the minus J7.5 flowing into ground, minus J7.5 per unit flowing into ground, that will pass like this in the ground, and finally it will enter into this one. It will enter into this one. Yes or no? This is minus J7.5 per unit current. And whatever the current minus J7.5 entering, that is getting divided between these three. It's getting divided between these three. Getting all of you? IB of G2 is how much? Minus J. No? It's minus J. I'm sorry. Minus J, and this is also minus J. I'm really sorry, I done a mistake. It is plus J. It is plus J 1.25. Okay. See, this minus J 7.5 divided between these three as minus J5, minus J 1.25, minus J 1.25. That summation will go in this manner. Summation will go in this manner. I think all of you getting this one? The circuit analysis are done? Yeah, it may be possible, Ramakrishna. It may be possible. Okay. So today we will stop at this point only. Today we'll stop at this point only. Tomorrow we'll take one problem on again LG fault. We'll take one more problem and we'll extend that thing. We have to discuss some more thing in the LG fault that we will extend in the tomorrow class. Yeah. So if anybody have doubts, you can ask me. You can raise your hands and you can ask me. Venkatesh.
Sir, 165 pin.
What is that number? 165. 165.
Yes, sir.
Okay, tell me.
Sir, in that phase 0 sequence, current is 0.15 is getting.
0.15. Tell me, what's your doubt, Venkatesh?
Sir, zero sequence current it is getting with the Thevenin's impedance.
Ah,
It is getting 0.15, sir. J 0.15.
J 0.15.
Yes, sir.
Zero sequence Thevenin impedance.
Yes, sir.
J 0.25, right?
Sir, it is J 0.05, sir.
Where? Which number?
In transmission line.
What is that number? What
0.1 is the
How much is given?
transmission line is 0.1, sir. J 0.
What is that 0.1 for transmission line? Venkatesh,
Sir,
tell me, Venkatesh, what is 0.1 for transmission line?
impedance, sir. X naught.
X naught. How much is X naught per line given in the data?
0.1, sir.
See in the data. I have displayed the slide also to you.
Okay, sir. Okay, sir.
Any other doubt you have, Venkatesh?
No, sir.
Jitendra. Jitendra.
Sir, in the last question that you have done now, you are
I'm unable to listen to you, Jitendra. Can you speak
Hello.
louder?
Hello.
Tell me.
Sir, in the last problem that you discussed today,
Ah,
wherein at the end you said that from the fault the current will go to the star ground. Yes, sir.
yes.
Sir, if this second generator also does not have a ground like this, it is also isolated.
That we'll discuss in tomorrow class. Isolated neutral system, single line to ground fault, we will discuss tomorrow.
Okay, sir. Okay, thank you, sir.
Okay. Viraj. Viraj. Yeah, I have given my mobile number already to all in this class. Many times I have given my mobile number. Just you put a text message to me. 96184619118. Just put a message to me in the Telegram. That is sufficient to meet your requirements or your doubts and all. Okay, just put a message to me in the Telegram. Else, just you put a message in regular message also. Okay, please tell me, Jitendra, I think your doubt was clear. Jitendra, please start.
Yes, sir, my doubt was clear.
Okay, fine.
Sir, just another thing. Sir, can you provide your protection notes, sir? Protection and LFC. Hello.
Okay, you ask the type of things personally. It's not.
Okay. Okay, sir. Yeah.
I think you have understood. No?
Yes, sir.
Any other things? Even this subject you have to ask live. Other things you should ask personally. Tulsi.
Hello, sir.
Tell me, Tulsi.
Sir, in 143, sir.
143.
Yes, sir.
Okay.
Sir, that generalization, can you please explain one?
That we have done one problem also, right, Tulsi, based on generalization.
Yes, sir.
That's it. What's doubt you have in that?
Okay. I didn't come.
See, we have done this problem, right? The generalization, the people are getting a doubt in that generalization only. That's why intentionally I have written this problem.
Okay, sir.
So we have a generator, transformer, line, and so on. I am asking you to find LG fault current with respect to midpoint of line.
Okay.
What you have done in that, you have calculated Z1 equivalent with respect to midpoint of line,
Z2.
Z2 equivalent with respect to midpoint of line, Z0 equivalent with respect to midpoint of line.
Yes, sir.
Taken the pre-fault voltage
And calculate it.
and calculate the fault current. Same thing we have displayed here. Yes or no?
Yes, sir. Z1 equivalent.
I'm saying that you calculate pre-fault voltage, then calculate Z1 equivalent, then calculate Z2 equivalent, then calculate Z0 equivalent. After getting all these numbers, if you want, you develop the Thevenin networks.
Okay,
Positive sequence Thevenin, negative sequence Thevenin, zero sequence Thevenin, connect them in series, make a short circuit, find out the current needed.
Oh.
Else, directly you put the numbers in this formula, you will get the LG fault current.
Okay, sir.
Okay.
Got it. Sir.
Hmm.
Sir, in 148 is sir.
148. Okay. tell
That
me.
approximate before page, sir.
Okay. Hmm.
Here impedances are converting into that neglecting the sir.
Impedance means R plus Jx, right?
Yes, sir. That one I understood, sir. Jx1 equivalent to నెక్స్ట్ వచ్చేసరికి x1 ఈక్వలెంట్ అయిపోయింది కదా సార్ అంటే మాగ్నిట్యూడ్ తీసుకున్నా కూడా అది
Magnitude, modulus of Jx is X only, right?
సార్ సార్ టోటల్ కి చేస్తున్నాం కదా సార్
J you take common. You say.
ఓకే సార్ సారీ సార్ ఐ గాట్ ఇట్
Okay.
సార్ అదే సార్ నాకు కూడా అదే డౌట్ వచ్చింది సార్ ఐసోలేటెడ్ గ్రౌండెడ్ తీసుకోము మనము అని చెప్పి 158 క్వశ్చన్ లో
We will see. We will see tomorrow. Tomorrow
Okay.
class. Tomorrow at the beginning stage itself, we are going to discuss about that only.
ఓకే
We'll take one problem and we'll see what are the consequences and what are the disadvantages with respect to ungrounded neutral system and all. Okay.
ఓకే సార్ థ్యాంక్ యూ సార్ దట్
Dinesh, you put a simple message to me, na? Simple message you put to me. Okay. Maybe in WhatsApp or Telegram or normal message I am saying. Vaishnavi,
హలో సార్
tell me, Vaishnavi.
సార్ ఇప్పుడు ఆల్టర్నేటర్ లో పాజిటివ్ అన్బ్యాలెన్స్డ్ ఆల్టర్నేటర్ ఉన్నప్పుడు పాజిటివ్ సీక్వెన్స్ లోనే ఇంపిడెన్స్ ఈఎంఎఫ్ అనేది ఇండ్యూస్ అయి ఉంటుంది కదా సార్ నెగిటివ్
Yes,
సీక్వెన్స్ లో ఈఎంఎఫ్ ఉండదు నెగిటివ్ జీరోలో కానీ ఆ రోజు సండే క్లాస్ లో చెప్పేటప్పుడు నెగిటివ్ సీక్వెన్స్ అనేది
ఉండొచ్చు. ఒకవేళ ప్రీఫాల్ట్ సిస్టమ్ కనుక అన్బ్యాలెన్స్డ్ అయితే ఉండొచ్చు.
సార్
In case if the prefault system is unbalanced,
ఎస్ సార్
then there may be a chance of getting the negative sequence and zero sequence prefault voltages.
కానీ ఇండ్యూస్డ్ ఈఎంఎఫ్స్ అనేవి ఎప్పుడు బ్యాలెన్స్డ్ అయ్యే ఉంటాయి కదా సార్ సేమ్ పాజిటివ్
See, where you are calculating that prefault voltage, is it at the terminal of the generators or you can say internal EMF of generator?
టెర్మినల్ వోల్టేజ్ సార్
Terminal voltage. Terminal voltage depends upon the preloading condition. Right?
ఎస్ సార్
If the prefault condition is the unbalanced one to you, even though your induced EMFs are balanced, terminal voltage will come unbalanced only, right?
ఎస్ సార్
Getting me? Or you want me to elaborate little?
ఎలాబరేట్ సార్ సమ్
See is an alternator. Your induced EMFs are balanced.
ఎస్ సార్
Induced EMFs are balanced. And this is EA, EB is balanced.
ఎస్ సార్
And this neutral is grounded. Now you see, it is connected to some network, whatever it is. Okay? And these are carrying unbalanced currents. IA, IB, IC are unbalanced currents.
ఎస్ సార్
Because of this unbalancing, these voltages at terminals VA, VB, VC are unbalanced.
ఎస్ సార్
Okay, now you have to do your fault analysis with respect to this terminal.
ఎస్ సార్
Now tell me, what are the voltages at the terminal before the fault occurrence? Is it VA, VB, VC or EA, EB, EC?
బిఫోర్ ఫాల్ట్ ఏఈబి
VA, VB, VC, right?
ఎస్ సార్
And you are saying yes, yes, yes.
సార్ నాట్ ఆడిబుల్ సార్
Listen.
హలో
listen,
సార్
Listen
Hello?
to me. Please listen to me.
ఎస్ సార్ ఎస్ వినపడట్లేదు సార్
See, your internal voltages are balanced.
ఇంటర్నల్ వోల్టేజ్ బ్యాలెన్స్ సార్ ఎస్ సార్ ఐ అండర్స్టాండ్
These generator phases are carrying unbalanced currents.
ఎస్ సార్
Because of that, the terminal voltages are unbalanced.
ఓకే సార్
Now I am saying this is my fault location.
ఎస్ సార్
Before fault occurrence, at the terminals of the generator, how are the voltages we have? Balanced or unbalanced?
బిఫోర్ విఏ ఈజ్ ఈక్వల్ టు ఏ ఇట్ ఈస్ బ్యాలెన్స్ ఉంది సార్
It's carrying some current, right?
ఎస్ సార్ అన్బ్యాలెన్స్డ్ సార్
Why unbalanced?
బికాస్ ఐఏ ఐబి are carrying unbalanced current so that
That's right, the
voltages
terminal
are.
voltages are unbalanced.
Yes, sir.
So these are nothing but your pre-fault voltages, right?
Yes, sir.
So these are unbalanced voltages. So definitely you have positive sequence component in the pre-fault, negative sequence voltage in the pre-fault, zero sequence voltage in the pre-fault.
Okay, sir.
But your internal EMFs of generator will be balanced only, right?
Okay, sir.
Getting me?
Yes, sir.
Yeah.
సార్ మరి ఇంకోటి మామూలుగా సార్ వస్తుంది సార్ ఇప్పుడు మనము సర్క్యూట్ బ్రేకర్ సార్ 1 సెకండ్ సార్.
Yeah.
సార్ ఫాల్ట్ లెవెల్ అని ఫార్ములా రాస్తున్నాం కదా సార్, వోల్టేజ్ ఇంటూ కరెంట్ అనేసి. ఫాల్ట్ లెవెల్ అంటే ఇప్పుడు మనము వోల్టేజ్ ప్రీ ఫాల్ట్ వోల్టేజ్ ఎందుకు రాస్తున్నాం సార్? ఫాల్ట్ వచ్చినప్పుడు వోల్టేజ్ అనేది అక్కడ చేంజ్ అవుతుంది కదా సార్.
No, the intention is to find out how much power is going. Okay.
What, sir?
How much power is going to be circulated during the short circuit fault? That's the aim there.
Yes, sir. Yes, sir.
To know about that, we have to use a pre-fault voltage only, right? Because that is the voltage of your circuit. Means your Thevenin circuit will have that voltage only, right?
Yes, sir. Yes.
Yeah.
Okay, sir. Okay, sir.
Okay. Any other doubt you have? You see?
No. No, sir.
Vaishnavi, sorry.
No.
Charan Reddy, Sai Charan Reddy. Sai Charan Reddy. Do you have any doubt?
Hello, sir.
Tell me, Sai Charan.
Sorry, you told when the source is balanced, we will take the positive sequence as positive and remaining all are negative. Is this correct, sir? Negative, not a
Remaining
zero.
all are zero, not negative. Yes.
So it is a standard. It is a standard assumption, sir.
Not standard. You convert your pre-fault voltage into symmetrical components.
So if we convert, then the negative sequence and the zero sequence.
If the pre-fault voltages are balanced, and if you convert them into symmetrical components, you will get only positive sequence component, right?
Yeah, yes, sir. Yes, sir. Yes.
That's it.
Sir, and today we mostly depend on symmetrical components to do problems now, sir. Almost all of them.
Because system is unbalanced.
Yes, sir. Sir, but it is taking more time, and we should proceed this method only for all the
This
exam.
method only. This method only, but you don't get lengthy problems in the exam, right? You get some simple problems only. You go through previous gate questions, Sai Charan once, then you will get a feel how we are getting the questions in the exam.
Yes, sir. Yes, sir.
Okay.
Okay.
Any other doubt you have, Sai Charan?
No, sir. And your lectures are very interesting, sir. Day by day.
Thank you. Thank you. Thank you. Okay. Next, Imtiaz.
Good evening, sir.
Good evening, Imtiaz.
Sir, in page number 156.
Tell me.
Sir, there is a problem, no, sir. In that, it said ZF is equal to 0.6.
ZF equals to 0.6.
Yes, sir.
0.2.
Right. Oh, yes, sir. 0.2. Sir, but it's not mentioned, no, sir. It's a reactance or resistance. How we can take
That
the
impedance, right?
resistance?
Imtiaz.
Yes, sir. It's impedance means both, no, sir. Reactance plus.
But he
resistance.
didn't say it's the magnitude of impedance. He said simply impedance.
Then it's considered as only resistance. sir,
0.2
at the
plus
time.
J0. 0.2 plus J0 I can write, right?
Oh, okay, sir.
Yes.
Okay, sir.
0.2 is a real number. I will write that as 0.2 plus J0.
Okay, sir. Okay, sir.
Okay.
Sir,
Impedance.
Okay. Sir, one more is there.
Hmm.
The normal general question, sir.
Hmm.
In the circuit breaker rating,
Hmm.
సార్ సర్క్యూట్ బ్రేకర్ నుంచి కరెంట్ ఫ్లో ఉన్నప్పుడు అది ఫేజ్ కరెంటే కదా సార్?
Yes, phase current. Line current.
ప్రీ ఫాల్ట్ అంటే ఒకవేళ ఫాల్ట్ వచ్చిన తర్వాత సర్క్యూట్ బ్రేకర్ ఎట్లా ఆన్ అవుతుంది సార్? అంటే యాక్చువల్ గా ఫేజ్ కరెంటే ఫ్లో అవుతాయి కదా సార్ ఫాల్ట్ వచ్చినప్పుడు?
Phase current means that is a heavy current now.
అంటే మోర్ దాన్ ఫాల్ట్
After the fault has been occurred, the resultant current flow in the what we call circuit breaker is very, very high in magnitude.
IF is more than IA.
Rated current.
Yeah, that's fair.
Your fault current is higher than your rated current, right?
Yes, sir. Yes, sir.
Okay, what's the doubt you have in that? Tell me, please.
I thought IA will be same at that time.
No. After the short circuit has been occurred, we have overcurrent circulation in the system. That overcurrent has to be interrupted by the breaker by taking the signal from relay.
Okay, sir.
Okay.
I got it. Yes, sir.
Hmm.
That's all. That's all.
Any other doubt? That's it.
No, sir. Thank you, sir.
Sridevi. Do you have any doubts, Sridevi?
Yes, sir. Good evening, sir.
Tell me. Devi.
Sir, ఇక్కడ fault current calculate చేసినప్పుడు you have added plus 360 degrees చేశారు కదా sir. For what
Hey, even you add 360 or not adding 360, it will be remain same now. I should get the option right. I don't have the option what I calculated.
option ఉన్నట్టు
Minus 210 degree, you don't have any option.
ఆప్షన్ ఇందులో ఇచ్చినట్టు ఉన్నాడు సార్.
Which one? You check the screen once.
లేదు సార్, plus 210 ఉంది సార్.
Plus 210 is wrong, right?
ఓకే సార్. సార్ వన్ మోర్ డౌట్ సార్. సార్ అది ఆ రోజు నేను మీకు డౌట్ అడిగాను కదా సార్, పాజిటివ్ అండ్ నెగిటివ్ సిమెట్రికల్ కాంపోనెంట్స్ ఎలా క్యాల్కులేట్ చేస్తాం ఫేస్ వోల్టేజెస్ ఇచ్చినప్పుడు అని. అది మనకి లైన్ టు లైన్ వోల్టేజెస్ VAB at an angle of some 0, VBC and VCA మూడు ఇచ్చారు సార్. మూడు ఇచ్చేసి స్టార్ కనెక్టెడ్ అన్బ్యాలెన్స్డ్ లోడ్ అన్నారు సార్. మనకి ఇప్పుడు పాజిటివ్ సిమెట్రికల్ కాంపోనెంట్స్ కావాలంటే పాజిటివ్ అండ్ నెగిటివ్ తీసుకుని జీరోవి మనం డిస్కార్డ్ చేయొచ్చు అని మీరు చెప్పారు కదా సార్. అది కూడా మనం డివైడెడ్ బై √3 చేస్తే పర్ ఫేజ్ వస్తుంది అండ్ ఇట్ ఈస్ హ్యావింగ్ అన్ యాంగిల్ ఆఫ్ -30 degrees టు ది గివెన్ యాంగిల్. అలా చేస్తే ఆన్సర్ రావట్లేదు సార్, ఎందుకంటే ఇక్కడ మూడు ఇచ్చారు కదా సార్, 3 లైన్స్ ఇచ్చారు, VAB, VBC అండ్ VCA. మామూలుగా మనం వెక్టర్ డయాగ్రామ్ వేసినప్పుడు ఇప్పుడు VAB ఇస్తే VA మైనస్ VB అలా తీసుకోవచ్చుని, లేకపోతే VA and
you send me that solution and as well as that question also. I will verify it.
సొల్యూషన్ చేయలేదు సార్, ఓన్లీ క్వశ్చన్ పంపించాను సార్. నేను సొల్యూషన్ ఇక్కడ చేశాను కానీ అది
You send me that solution also, Sridevi. I will correct it where you have committed mistake. Okay.
Okay sir. Okay sir.
Any other doubt you have, Sridevi?
No sir. No sir. Thank you so much.
Okay, fine. Yogashri.
Sir.
Hello, Yogashri.
Sir, starting లో మీరు VA plus VB plus VC is equals to 0 అన్నారు కదా సార్. సార్ అందులో నెగటివ్, దాంట్లో వోల్టేజ్ నెగటివ్ వస్తే అప్పుడు మైనస్ వస్తుంది.
VA plus VB plus VC is 0.
సార్ నెగటివ్ సీక్వెన్స్ దాంట్లో నెగటివ్ వోల్టేజ్ వస్తే అప్పుడు నెగటివ్ వస్తుంది కదా సార్, -VB అని.
It won't be like that.
అంటే మైనస్ రాదా సార్?
Have you taken any numerical like that? Do you have a numerical in that manner?
Numerical means
do you have any example to say on that?
సార్ నెగటివ్ వోల్టేజ్ సీక్వెన్స్ వెళ్ళినప్పుడు -VB అనేది అయితే వస్తుంది కదా సార్, అట్లా అని అడుగుతాను.
Not -VB, Yogashri. It is VA plus VB plus VC. Means VA is VA1 plus VA2 plus VA0. Okay, VB means VB1 plus VB2 plus VB0. Similarly, VC.
నెగటివ్ ఫ్లో అయినా కానీ పాజిటివ్ తీసుకుంటారా సార్?
What is that flow you are saying me? We are dividing voltage into 3 parts. Such that VA equals to VA1 plus VA2 plus VA0. That is our standard conversion. Why you are getting that negative? How you are taking that negative spelling into mathematical term?
Means negative sequence means I thought voltage.
It is not negative value. It's not negative value.
Okay.
It's not negative value. We are converting phase A voltage into 3 components. Such that phase A voltage equals to positive sequence voltage plus negative sequence voltage plus zero sequence voltage.
Okay, sir.
Okay?
Okay, sir.
Tell me any other doubt you have?
No, sir. I clarified the doubt. You told Esther tomorrow you will tell no, sir. That.
Yeah.
Yes, sir.
Jay.
Hello, good evening, sir.
Good evening. Tell me, Vijay.
Sir, in general, we in triple LG fault, we taken load current into account and calculated accordingly. How we are incorporating load current into LG fault, sir?
Similar way. For phase A current, you have to add that. Fault. For phase A fault current, you have to add load current.
Okay.
Just additional subtractions. Whatever we said earlier, same procedure we have to adopt to remind all types of faults.
Okay. That means if I have to calculate individually the current supplied by for an individual generator or something like that, I have to add that load current.
Pre-fault current to all the 3 phases.
Okay. Okay. Thank you. Another doubt was, sir, we have calculated in the last page, we have calculated taking both generators into account at a time. Means if we calculate the impedances individually, supposing that generator 1 and generator 2 supplying the fault current individually, then the fault current, if I go through the diagram, generated in which IA0 is equal to IA1 is equal to IA2. In that case, the current supplied by that generator will be 0.
You tried. As already you are saying both generators are parallel.
Okay.
You have to draw positive sequence separate, negative sequence separate, zero sequence separate. Then we have to connect them in series.
Okay, that means I have to take
individually, right? Not individual connections. You should not do that.
I have to take whole network into account at a time.
Whole
right,
network. That's what we said. Positive sequence Thevenin network you have to construct. Negative sequence Thevenin network you have to construct. Zero sequence Thevenin network you have to construct. You have to connect them in series.
Okay. Thank you, sir. Thank you.
Okay.
Thank you, sir.
Yogesh.
Hello.
Tell me, Yogesh.
Yes, good evening, sir.
Good evening.
Sir, actually, I had doubt in yesterday's problem, sir. Sir, that in those 4 motors were in parallel, sir. Yes, sir. In that we have taken that EG generator voltage is equal to EM voltage, sir. Sir, that step I did not understand.
You take EG, EM both are equal because there is no current flow. There is no current flow
at fault,
right? Tell me, Yogesh.
Yes, sir.
Tell me.
Sir, when fault will occur, that time current will be there, no, sir?
After fault we have, but EG and EM we are taking in pre-fault conditions, right?
Sir, then in pre-fault condition, then it will supply.
Before occurrence of the short circuit, your system is at no load condition, operating at rated voltage. Yes or no?
Yes.
Then what is the rated voltage of your system? 11 kV by √3 per phase.
Yes, sir.
As you don't have any current flow in your system, all the voltage sources in your system will have the same voltage.
Okay, sir.
What I have written as generator voltage and motor voltage. What's the doubt in that again?
Okay, sir, got it.
See, don't be in a feeling that after the fault has been occurred, the internal EMF will become zero. How the internal EMF will become zero? It's a
No, sir.
voltage source, right?
Yes, sir.
After the fault has been occurred, whatever the voltage you have at the fault location, that will become zero.
Yes, sir.
Okay?
Yes.
Tell me, Yogesh, any doubt you have?
No, sir, that only. No, sir.
That only. Clear now?
Yes, sir. Yes, fine.
Yeah, fine. Rosemary. Rosemary. Do you have any doubt? Rosemary? Please kindly respond. Naveen Kumar Reddy. Naveen Kumar Reddy. You have any doubt? Naveen Kumar Reddy?
Hello, sir.
Tell me.
Sir, once explain CRO 18th question, sir. I texted
Can
you.
you read that question once?
That's circuit breaker rating.
Circuit breaker rating.
I had posted in Telegram, sir.
Okay, okay.
For the configuration shown in figure, the breaker has a loss.
Hello.
This one?
Yes, sir.
Can you read it? For the configuration shown in the figure, the breaker is connecting to a large system at bus 2. Bus 2, and it is initially open. The system 3-phase fault level at bus 3 under this condition is not known. Fault level is unknown at bus 3 after the system has been disconnected.
Yes, sir.
After closing this breaker, the system breaker was closed, then the 3-phase fault level is 5 per unit, he said. Means fault current is 5 per unit after the breaker was closed.
Okay, sir.
What will be the new 3-phase fault level at the system? Bus 3, system bus 3, after this interconnection, all per unit values are in per unit common basis. Sorry. Default load currents are neglected, default voltages are assumed to be 1 per unit. Okay. Okay, this is a system given. Huh? We have 1 minute, please wait.
Hello.
1 minute, please. Yeah, see this. First three, this condition is not. See, actually, what he's saying is, this is your initial state of system. You have one generator connected to to this. See, it is open, first of all. It is open. And you don't know fault level at bus 3. That's what he said first. Yes or no? Are you there, please?
Yes, sir.
Yeah. For the configuration shown in the figure, the breaker connecting a large system to bus 2 is initially open. Means this breaker is open. That's what I have shown here. Okay. So after the breaker has been opened, the system 3-phase fault level at bus 3 is unknown. Means at this bus, means bus 3, at this bus fault level is unknown for us.
Yes, sir.
Fault level is unknown. Okay, next step. After closing the system breaker, 3-phase fault level at bus 1 is 5. So I will say this is a system. Breaker was closed. After closing the breaker, fault level at the bus number 1. Bus number 1 fault level is 5 per unit. Okay.
Yes,
so
sir.
what is this 5 per unit actually? Per unit fault current magnitude.
Okay.
Means you first represent your generator with the voltage source and reactance. And then you have transformer. And then you have a line. And then you have a system. And this system is going to represent as a voltage source in series with the reactance only by Thevenin model.
Okay.
Okay, so this is a system reactance, and we have a voltage source for the system also. And this is a bus 1.
Yes.
This is a bus 1. Okay. And what are these reactances given for generator? Generator reactance is a 0.2. Okay. Transformer reactance given 0.2. Line is given 0.3. And excess is unknown. System reactance is unknown. Okay. So with respect to bus 1, if you find out that Thevenin equivalent reactance, how much you will get? With respect to bus 1,
0.5 in parallel.
X equivalent will be how much? 0.4 in
0.4
parallel
in parallel with 0.3 plus
excess.
excess.
0.4 in parallel with 0.3 plus excess.
Yes.
What is fault level formula?
3 times of
Fault level formula.
3 times
Which
of
fault is
pre-fault.
it?
3-phase short circuit fault.
3-phase short circuit. 3-phase short circuit means simply pre-fault voltage by X equivalent you will get.
Okay.
Okay. What is fault current? Thevenin voltage by Thevenin reactance, right? That's it. As it is the balanced system.
Okay.
Now this is 5. 5 is equals only magnitudes I am considering. 1
Okay.
by X equivalent. So X equivalent value must be equals to 1 by 5.
Yes, sir.
Okay. So after saying that X equivalent is equals to 1 by 5, you substitute that X equivalent here. Let's say like this. 5 is equals to 1 by 0.4 plus 1 by 0.3 plus excess. Na?
Yes, sir.
And you calculate excess value from this one.
Okay.
How much you will get? 1 by 0.4 is I think 1.25. 5 minus 1.25. Do that quickly. Tell me excess.
Just a minute.
Yeah. How much?
Just a
How
minute.
much time? Huh?
Just-
Me. Are you getting or not?
Getting, sir.
How much?
So just a minute. Minus 0.3.
Get negative number.
Minus 0 point.
Don't get negative number. Just check back once. What's the data they have provided? Point to point. After this introduction. Not 0.4.
0.1, sir.
0.1 you are getting.
Yes, sir.
It's 1 by 0.4, 2.5. 0.4. Yeah, okay. 0.1 is the excess value.
Yes, sir.
Then what is asking further?
Short circuit MVA at
Yeah, which
bus
was?
3.
Bus
Bus
3.
3.
When? After doing connection or without connection?
After interconnection, sir. After
I have done the
connecting circuit
interconnection.
breaker.
I have done the interconnection.
Yes, sir.
And I have to find the fault level at bus 3.
Yes, sir.
All the reactants are known. Excess is also known now.
0.1. Yes, sir.
Then what is the X equivalent value?
0.7 in parallel with 0.1.
Parallel with 0.1. Calculate this number and find out fault level.
Yes.
Default voltage by new X equivalent at bus 3. 1 by this number. How much is it? 0.0?
875.
875. Get it.
Thank you, sir.
Any other
11.4. 11.428.
11.428.
Yes, sir.
Okay.
Hello.
Thank you. No doubt.
Hello.
Tell me, Mary.
Sir, am I audible?
Yeah.
Sir, in the first slide today, sir, there was, how did you get Z0 is equal to J into XL?
Yesterday, we have discussed that in the previous classes, right? In the symmetrical sequence networks, we have discussed about it.
Okay, sir.
It was taken from previous classes.
And in slide number 164.
Okay.
164, sir. Here, how did you get? I had a doubt on how you got Z0 equal to 0.25 J.
No, from this point, you should check what is the equivalent impedance, right?
Okay. Sir,
you inject one current here.
Okay, sir.
Harry, inject one current. Check in what path that current is flowing. It won't flow in J0.15. It should flow only in this path, right?
Okay, sir.
So this whole impedance is nothing but Z equivalent value.
Okay. Okay, sir. I got it. Thank you. Thank you, sir.
Fine.
That's all.
Anil.
So good evening, sir.
Good evening. Tell me, Anil.
Sir, in this problem, we are calculating the sequence current that one please explain, sir.
Yeah.
Next slide.
Next slide.
Yes, sir. The zero sequence current I didn't understand.
The sequence?
It's current, sir. So in one of the question, they are asking to find a neutral voltage. For that purpose, we are calculating that.
You calculate zero sequence current. Okay.
Sir, I did not get that. We are calculating zero sequence current.
Because we have to find neutral voltage means that is available only in zero sequence network, right?
Okay, sir. Okay.
For that purpose, we calculate IR0.
Okay, sir. Okay. Okay, sir. Sir.
Yeah.
Thank you, sir.
Any other doubt here, Anil?
No, sir.
Okay, thank you,
sir.
Madhu. Madhu.
Hello, sir.
Tell me.
Sir, I have a doubt from star delta and star ungrounded connections.
Delta and star?
Unground connection. So 3 days back tapped. Sir, Sir, in those connection, we do not have any closed path, sir. And how can we say third harmonic currents will be there in the circuit?
Delta, inside delta loop.
Sir, in the circuit, both sides will be open, no, sir. There will be any closed path.
That circuit you have drawn only for zero sequence current flow, right?
Yes, sir.
Third harmonic is a different one.
Okay, okay.
Whatever the circuits we have drawn there, those are valid for only our zero sequence, not valid for third harmonic, right?
Yes, sir.
Mm.
Okay, sir.
Okay. Any other doubts? Please raise your hands. Any other doubts? Good. Bharati. Bharati.
Hello, sir.
Tell me, Bharati.
Sir, in the last problem, you did know, sir, like fault level is equal to V pre-fault by X equivalent. How is that formula, sir?
Fault level means what? Fault current only, right?
Yeah, yeah.
For three phase fault current will be pre-fault voltage by Thevenin equivalent reactance. Per phase mode only. It's a three-phase fault. The difference you have to understand first. It's not LG. It's a three-phase fault, right?
Yes, sir. Yes, sir.
Yeah.
Okay. Okay, sir. Thank you, sir.
Mubin.
Hello, sir.
Mubin.
Sir, we have that did 210 angles we got na sir, minus 210. So we did 180, 360 minus that angle. So we get 150 na sir. In that,
yes.
Sir, since it is star, the phase and line phase angle will remain same, sir. I mean, if generally we know that if phase angle is at some theta degrees, then the line angle will be 30 degrees leading for star and 30 degrees lagging for delta, like that.
For what? For what 30 degree lag? For what 30 degree lead?
Networks we study now, sir. Phase and line voltage will be like that.
Voltage. What you are calculating there?
Phase and line voltages, sir.
What you are calculating there? The 360 degree addition, what you asked?
There not problem, sir. I'm just that in that problem we are did like that, na sir.
Which problem? Wait, which problem?
Yes, sir. Yes, sir. One second. Sir, we have calculated VB. Sorry, not VB. Sir, actually, my doubt is this one only. In that, everything is clear. My doubt is this one only. We found phase voltage, sir. For example, in the last problem, we found V neutral, not V neutral. Sir, did you understood what I want to ask?
You tell me in which problem you have a doubt.
No, sir. All problems are clear, sir. Just I got general doubt.
See, if it is a balancing system for you, and if you want to convert your phase voltage to line or line to line voltage to phase, definitely you have to take care of the 30 degree shift. Okay?
Yes. Sir,
but if it's a current, your line current and phase current will be equal, no, in the transmission line wire.
Yes, sir.
Yes.
Sir, if we got EA per unit is equals to 1.1, 1.2 like that, sir, then what would be the EA line, sir?
It is per unit, magnitude will remain same. Angle
yes.
should say plus 30 degree.
Yeah, okay. That clarity only I need, sir.
Okay, fine.
Okay, thank you, sir.
Okay. Suresh.
Sir, in the generator one neutral voltage, you should write now VN1 is equal to VN0. Sir, please watch that page in.
What you have done in that?
Sir, how we find the generator one neutral voltage?
KVL application. Suresh.
Generator one.
Generator 1 voltage only I have shown here. KVL application.
Sir, understood, sir.
Tell me, any doubt you have? I will explain again.
No, sir, no, sir.
Vaishnavi.
Hello, sir. 181, sir. Page number. ఇందాక లాస్ట్ ఈ ప్రాబ్లమ్ లోనే సార్ లాస్ట్ లో అదే సార్ ఫాల్ట్ లెవెల్ అంటే వోల్టేజ్ ఇంటూ కరెంట్ ఇంటూ ఎస్ బేస్ సార్ మీరు వోల్టేజ్ పై
వోల్టేజ్ ఈజ్ 1 per unit. I have taken fault level in per unit form.
సార్ లాస్ట్ లో సొల్యూషన్
What is formula for fault level in per unit form?
వోల్టేజ్ ప్రీ ఫాల్ట్ వోల్టేజ్ ఇన్ పర్ యూనిట్ ఫామ్ ఇంటూ ఫాల్ట్ కరెంట్ ఇన్ పర్ యూనిట్ ఫామ్.
That's it.
Yes, sir.
Pre-fault voltage is 1 we are assuming. Then it will be IF per unit only, right?
సార్ ఒకసారి లాస్ట్ పేజ్ సొల్యూషన్ పేజ్ ఒకసారి చూపిరా సార్.
Okay.
ఇక్కడ సార్ V per unit by X equivalent వేశారు కదా సార్.
That is the fault current magnitude.
Okay, fault current magnitude. Okay, sir.
In case of three-phase fault, pre-fault voltage by Thevenin equivalent reactance is the fault current.
అంటే నేను ఫాల్ట్ కరెంట్ అంటే MVA అట్లా అనుకుంటాను. ఫాల్ట్ లెవెల్ అన్నారు కాబట్టి
fault level you can treat that as per unit MVA or per unit current, anything.
మరి ఇక్కడ ఎందుకు సార్ పర్ యూనిట్ MVA కన్సిడర్ చేయలేదు?
I am dealing with currents here. That's my wish, right? What to treat?
Okay, sir.
Either I can treat that as a per unit MVA or else I can treat that as a per unit current. That's my wish, right?
ఇక్కడ మనకి రియాక్టెన్సెస్ తెలుసు కాబట్టి మనం ఇట్లా ఫాల్ట్ లెవెల్ ఇన్ కరెంట్.
My interest is to find those reactance values, right? Reactance values and fault level again.
Okay.
That's why I considered to do this problem in currents.
Okay.
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 That's it. Any other doubt here?
No, sir. No, sir. Iదే sir doubt వచ్చింది. Okay.
If anybody have doubts, you can ask me. Please raise your hands if anybody have a doubt. Murali Krishna.
Hello.
Tell me please.
Sir, good evening, sir.
Good evening.
Sir, అదే సార్ ఇందాక మీరు మొబైల్ నెంబర్ రాశారు సార్, దాని బిఫోర్ స్లైడ్ లో సార్ ఇక్కడ అక్కడ -J 2.5 అది
-J 2.5
సార్ ప్లస్ ఇక్కడ రాసినారు కదా సార్ -J 1.25 ఇంటూ ఆల్ఫా
yes.
ఇక్కడ కింద వచ్చేసరికి అది J 1.25 per unit ఎట్లా సార్ అది?
Alpha plus alpha square value -1, right?
సార్.
You calculate it.
ఓహో.
Getting?
సరే సార్. ఓకే సార్. ఓకే, థ్యాంక్ యూ.
Yeah. Anybody have doubts? Can raise your hands. Anybody having a doubt? Please kindly raise your hands. I think I can leave. Nobody has raised your hand. Thank you.